Okay, let's start. So good morning, everyone. I am Sandrine Blasi, the General Chair. I'd like to go to the next slide, but it does not work. Okay, welcome in Rennes. I hope you will enjoy the city. Many events are planned this week and are co-located with POPL'. We already had 3 co-located conferences. There will be 9 workshops as well. Most of them will be live streamed and recorded. We also had 9 tutorials. And today and yesterday we had 4 young researcher focused events. So we have 2 mentoring workshops yesterday. Tomorrow, 2 days there will be the mentoring lunch. The student research competition will start as well. And there will be as well 7 social events. So yesterday we had a game night. Today there will be the reception, the women's dinner. There will be also special lunches. And on Thursday morning you will have a guided tour of the historic city center for those who registered. And there will be a lecture on the history of this convent here in this room on Thursday morning. So we worked hard to make this event happen and to organize all these things. By we, I mean a whole team I would like to thank. First of all, special thanks to Neringa, Mariana, Vaida, Lydie, and Aurélie. You should have met them when you registered. They will be in the atrium the whole week. Please do not hesitate to come and to talk to them, just to say hi or to need for help. I would like to thank as well all the staff of this place, Couvent des Jacobins, who helped us set up everything and arrange all the rooms you will use this week. There were more organizers I would like to thank. Michael and Benoit, the industrial relations co-chairs, Joe and Yannick, the web co-chairs, Nenning, the publicity chair, Hannah, who will organize the mentoring lunches today, Robert and Alan, the workshops co-chairs, Ralph and Catherine, the student research competition co-chair, Calvin and Vadim, the artifact evaluation co-chair, and Conrad Watt, the virtualization chair. We had more chairs. I would like to thank as well Yannick and Andrew, the PLMW co-chairs. I would like to thank the AV team, Nicola, Chris, Dexter, and Samar, who are doing a fantastic job to have everything fine here in all this room. And I would like to thank as well Aurel and Stephen, the chair for the student volunteers. They selected a lot of volunteers that you can see here. Do not hesitate to talk to them. They are wearing these blue t-shirts and they know the building better than you do. I would like to thank as well the program committee. First of all, Suresh Yaganathan, the PC chair for POPL', and the 5 associate program chairs, Colin, Laura, Robert, Sam, and Stephanie. Last, I would like to thank all the sponsors. And I'd like to remind you that POPL' is a sick plan conference, so there is a code of conduct that you can read on the website. So POPL' is a harassment and discrimination-free conference, and please contact me if you have any code of conduct concerns. There is as well sick plan cares that is available to support community members who have experienced harassment, discrimination, or bullying, and they're also available to provide information on how to report unacceptable behavior. Here are the people from Sick Plan Cares, and 2 of them are here this week, Jeff Foster and Stephanie Weirich, so you can come and talk to them. A few words about logistics. So for those who were here yesterday, we completely changed the configuration of the building. We will use new rooms. This room, the nave, here. So here we will mainly use rooms on the ground floor. So we are now in nave. There is as well a second room with a refectoire, which is here very close to this one. And there will be a third room for POPL' upstairs, just above refectoire. So we will have a coffee break in Hall 0 at the ground floor as well. And this is where the reception and the student research competition will take place this evening. We will use as well the first floor, the dortoir room, and this is where we will have lunches as the day before. And we will use as well another room for special lunches, which will happen on Thursday and Friday. Some schedules notes, so don't forget the reception this evening in Hall 0. There is as well a women's dinner in a restaurant in Rennes. So there will be a depart organized from Atrium 10 minutes before at 7:20. And tomorrow morning, so there will be 2 social events. So the lecture here in this room of the convent, and also the guided walking tour. For those who registered to the walking tour, so it will start at 9 and the building will be closed at 9. So the meeting point is in front of the tourist office, which is just there. So please just be there at 9 and then the tour will start. So I would like to thank you all for being here. Please enjoy the amazing technical content of the conference. I hope you will have some great discussions with your colleagues, and please make POPL'26 a memorable experience. So now let's listen to the first keynote. So there will be 2 keynotes this week, and they will be mirrored in the other room. So if you prefer to go to the other room, you can do it as well. It is my pleasure to introduce Damien Pousse, who is a senior researcher from CNRS. Damien is a member of the LEAP laboratory in Lyon, where he's leading a team of experts in logic and semantics, working on improving our understanding of proofs and programs. Damien got his PhD from ENS Lyon in 2007. He did a postdoc at UPenn, and then became a CNRS junior researcher in Grenoble and in Lyon. In 2016, he got an ERC grant, and 1 year after, he became a senior researcher. So during his PhD, Damien worked on concurrency theory. This inspired him to develop new algorithm and proof techniques to improve deductive verification and to apply them to concrete problems. He has worked on a number of topics, such as automata algorithms, clean algebra, co-inductions, and cyclic proofs. He also contributed to several work formalizations related to relational algebra, partial orders, graph theory, and categories. Today, we'll talk about medium-scale automation for proof assistance. So, Damien, I'm glad to have you here today.
Thank you. Thank you, Sandrine. Thanks to POPL for inviting me. Thanks to you for being there. I'm quite honored, impressed, delighted to be here in this beautiful room. And today, I'll just start a timer. I'm willing to talk about automation in proof assistance. And actually, a better title for my talk is this. I want to do better proofs using proof assistance and using some automation. So what does it mean to be a good proof? This is the first question. And the second one is why do we need proofs? And my claim is that we need proofs to convince people that something is true, to convince people about why something is true. Okay, so correctness is not the only thing. So a good proof should be correct, but more importantly, convincing. You can have proofs which are convincing but not correct. So that's not so nice. You can also have the converse, sadly. Another criterion is being concise, okay? Because it's easier to convince someone with a short proof than with a very long proof. However, there are constraints. Some problems are inherently complicated, and we know that there are statements whose smallest proof is arbitrarily long. Okay, so you cannot be always concise, but you should strive for conciseness as much as possible. And there is a balance here, right? If you want to be correct, you need to provide all details. If you want to be convincing, probably you'll need to elude some details which are too boring. Okay. First criterion is being reusable. You want your proof, certainly, to be reused by other people. And here I don't mean the statement of the theorem, I mean the proof itself. A nice proof often contains interesting ideas which you want to reuse somewhere else in other contexts. So proof should be reusable. First point on correctness. For quite some time, it was not that easy to have correct proofs. And it was rather subjective. Right? The proof is correct because I didn't find flaws, because I trust the authors, and so on. Nowadays, with proof assistance, we can do better. It suffices to trust the proof assistant, which is quite nice, actually. There is still a notion of trust. I mean, the proof assistant could be flawed, your formalization could be flawed, but still, I think nowadays we can assume proofs are correct. And this is very nice because once a proof is correct, we can make it more convincing, more easily. Now, how to make, what is a convincing proof? A proof is convincing, your proof is convincing, if I can understand it. Or maybe I can explain it again. It's also convincing if I can use it and adapt it to other needs. Right? And these two criteria, they also work for programs. Proofs are programs, remember. So a program is convincing if I can understand its code, if I can use it, if I can adapt it to other needs. There are possibly correct, yet very unconvincing proofs and programs in the nature. And let me discuss a few of them. One category is the write once, read never proof or program. This is a proof or a program which you've spent a lot of energy and maybe a lot of fun writing, but it's so complicated that no one will read it. Example. My first ray tracer. This is a very fun program, but the code is awful. It still works. I could get this picture, but I would not adapt it, right? Second example, your first submission, maybe. Or maybe the appendix of your last paper. And unfortunately, many formal proofs are like that. Since we have correctness, once it compiles, we push on Git, and then we forget about it. And we cannot read it anymore. And this is not good, right? You need your proofs, even your formal proofs, to be readable, reusable, and so on. Another category of proofs which are not completely okay, but still wonderful, are the read-only proofs. Proofs which are there, you can use them, you can understand them, but you cannot reuse them, you cannot adapt them. Here is one. Here is a very convincing proof that you can put 8 queens on a board without them eating each other. It's concise, it's convincing, but if you slightly change the statement, it's useless. Right? Another one is this small program to compute the inverse of square root. It's some code which is in the video game Quake 3, for those who know. And it only uses a few multiplications, and you get the square root with a fairly decent amount of decimals. So this is like magic. And it works. You can use it. It's sufficient for a video game, but you cannot use it in other contexts. Yet another one is this proof of irrationality of zeta of 3 by Aperi. He came up with this very strange formula, and a bunch of other ones. And using this magic formula, you can prove irrationality of zeta of 3. But this formula came from an oracle. I mean, you don't know how to adapt it, how to make it work for zeta of 5, maybe, or something like that. And again, when we do some formula proofs, some of our proofs are like that. We use some complicated techniques. They happen to work. We don't know why. They just worked. We didn't think about it, and we left it in this way. And then the proof, is very fragile. You try to adapt it to something else, and it fails, and you don't know why. And this is not good. Still, there are cases where you can improve the situation. In those three examples, basically, we had oracles. And here, for the first example, the oracle is certainly a SAT solver. So a better proof for this statement is the same proof together with the comment, I got the solution with the SAT solver, and here is the script I used. Because if you have this, then you can easily adapt the script and maybe hope for a proof of a slightly different statement. Here, I don't know what you can do. Here, maybe you can add Aperi's phone number next to the proof. Okay. So the challenge for me really is to make it easier to write convincing, concise, and robust formal proofs. Concise because it makes it easier to be convincing and to be robust. If you want to maintain a proof, if you want to adapt a proof, it's better if it's concise. And robust because you want to experiment with your proof, move it a little bit, and it should still remain a proof. Okay. So outline of the talk, I'll do two case studies, one in relations and one with monads. And in both cases, the game is to find the right abstraction level and to design and use appropriate infrastructure to work with these abstractions. So for relations, it will be regular expressions, clean algebra. For monads, it will be monoidal categories and string diagrams. Okay, so let's start with relations. I want to prove this very small, very basic theorem, maybe it's just a lemma. If two relations are transitive, then so is their composition. First, I have to define transitive. So I could use a definition like for all x, y, z, related by R, there exists, by R and then, anyways, a relation definition with points. This is painful, I cannot even do it right now, I'm too stressed. But you can also say a binary relation T is transitive if TT is below T. T square is below T. Okay. Second step is to fix the statement. My statement is completely wrong. Did you see it? Yes. Okay. You need an assumption. And this one is sufficient. If S and R commute, then you're fine. And then you can write your proof. So this is a paper proof. I find it concise and convincing. Right? You swap S and R in the middle, and then you use transitivity of R and transitivity of S, and you're done. Now what I want to do is to have the same form of concision and convincedness in the proof assistant. So let's do it. Is it big enough for those in the, yes? Okay. So here's the statement of my theorem, or lemma. Okay. And here is a first proof. What do? I want to I want to swap S and R in the middle. Maybe I should display the goal here. I want to replace SR with RS. For this, I have an hypothesis, but I cannot use it right now. Right? There are parentheses which I should reorder in order to be able to do my rewrite. This is a bit painful, so I do it. I put parentheses right, then I rewrite. Okay, I get there, but now I want to replace R by R and SS by S. Again, I do have hypothesis for this, but I have to mess with parentheses before I can do it. I do it, and I'm done. This is a concise proof, but it's not satisfactory, right? You don't want to have those intermediate steps to deal with parentheses. Also, it's really not robust. Maybe if I set up a new notation to change my to make my statement more concise. Okay, I want the square of a relation, and now I want to state everything with squares. This is the same, right? But now my proof breaks. I don't want this. I don't want a proof to behave like that, right? I want something which is robust with respect to this kind of change of notations. Okay. So let's do another one. Here's a second proof, a bit longer, a bit more explicit. I say, well, first thing, I want to replace SR with something. So let me make it appear explicitly with the transitivity step. And this, then I get two goals. One which is easy because it's just about parentheses, and I can solve it with some tactic. And the other one, which is the one where I can rewrite. Okay. Same thing for the other steps. I can message the goal explicitly to be under a shape. I can use it. So here I want RR and SR, and SF. Again, erase of the goal. I could even have used my notation here. And then I can do my two rewrite steps, and I'm done. This is more robust, but this is less concise. And it's a bit painful to type those terms with parentheses. So what can I do? I can do a third proof with some more automation. Here I have access to a tactic mrewrite, which does perform rewriting modulo associativity, so that I don't have to care anymore. And I just do the 3 steps which were on the board before. And this proof I find concise, convincing, and robust. So this is the kind of proof I aim at. Okay. Let's do another one, slightly more complicated. Here's a small lemma, again, a bit bigger about relations, about reflexive transitive closure. And the proof below in Isabelle, which is correct, a bit long. You can still get some insights by reading the proof, but the statement is too simple. You don't want a formal proof to be that long. What else can you do? You can call the literature. There are theorems. In particular, there is this one. The equational theory, the equational theory of relations, restricted to regular expressions, is decidable by this characterization. 2 expressions are equal if and only if they denote the same language, are equal in the relational models. And deciding language equality is okay. There is an algorithm for it. So you can code this algorithm. And since you are in a proof assistant, you can even certify this algorithm and execute it inside the proof assistant to get proofs. This is called reflection. So using reflection, you can use your favorite decision procedure in order to solve your favorite problem in a certified way. So this proof, which we had before, nowadays, we can just, here it is. We can just prove it with a tactic. KA, for clean algebra, solve this goal immediately by running an automata computation. This is concise. This is convincing if you believe the theorem. I mean, if you understand the theorem that says that you shouldn't care about such equations because they are decidable. And it's robust because now if I change something, I don't know, if I swap two things in my statement, the same proof works. I don't have to go into the proof to find where I had to use R and not S and rename all my hypotheses and so on. Okay. And you can do other examples like that, which I'll skip for now. Okay. Another example, if you want to study confluence or commutation of relations, of maybe rewriting relations, certainly you have encountered this lemma, Church-Rosser, which says that if two relations commute strongly, then their reflexive transitive closure also commute. You can state it algebraically in a very natural way. And when it comes to the proof, you need an intermediate lemma. You need to do the two stars one by one. And the two steps are proved by induction. Certainly, you have seen these proofs many times. And again, I want these easy proofs to be really easy in a proof assistant. So what can I do here? This is my lemma. This is, sorry, the theorem, actually, the first line. And then there is a lemma. I want to prove this lemma inside by induction on the star. Actually, the star which is on the left. So I start my induction. Up. Base case is trivial. This is just Ka. And inductive case, you have to use your hypothesis. You can do it modulo associativity. There. And then you conclude by Ka. Up. So you have the lemma. And now the theorem out of the lemma will be the same, except that I do an induction on the right. Base case is again trivial. Now you have to use the lemma inside, and you're done. Okay, so this is good because it's again concise and rather convincing. You get not much more than the intuitions that were on the slide. And is it robust? And I claim it is. For instance, you may know this variant of the lemma. If you have a reflexive closure here and a transitive closure here, it still works. So can we adapt the previous proof? Yes, we can. So here I just add my, say, let's do the star first. I add the star here, and I think the proof just completely goes through. Because Ka, the tactic, takes care of it. So it's automatic. Now if I want to add sorry, this is not here, the reflexive closure here, it's a bit more complicated. The proof fails. It fails by saying, oh, look here, this is not a theorem. This is not a theorem because one, the empty word, is accepted here. No, the goal is not synced. One is accepted here on the left, but not on the right. You see that there is an error here. So I should look at my proof and understand what failed. And in fact, what failed is that I should fix my intermediate lemma also for the proof to go through. And it still doesn't work because here I introduce some a case distinction which has to be there, but I can easily fix it. I don't explain you why, how, but you can easily fix it. And then you're done because the rest of the proof goes through. So here, the same proof doesn't work, but I can easily adapt the proof to make it work. This is what I call robust. Okay. So, was this convincing, concise, and robust? Concise, yes. Convincing, you have to accept that you can abstract away all details about regular expressions. But besides this is okay. And robustness, I think it's robust because the KA tactic solves a very well-defined problem, and there is a complete algorithm for it. So either it succeeds or it fails, and when it fails, you know why. And this is very important for robustness. Okay. For reusability, another important thing is abstraction. You need to state and prove your results in the most general form, right? And here we can use the strengthening of the previous theorem to do that. This is a theorem I've shown before. In fact, there is an algebraic version. Not only the equational theory of relations is decidable, but actually the equational theory of all linear algebras, which is an axiomatic system. And this theorem makes it possible to apply the previous techniques not only to binary relations, but actually to any linear algebra. And the proof which I've done before, they would scale without doing anything to an abstract context where now the statements would be about elements in a linear algebra. Let's see this. Actually, if here at the beginning of the section, instead of assuming that I have a type and a few relations, I assume I have a structure. Here it's a partially ordered monoid, and elements of it. The same proofs will just go through, all of them. Well, all of them, except at this point where here you use KA, the linear algebra structure. So you need to have it, and this I say it in this way. Okay. So by moving to an algebraic framework, I can extend, this time not the usability of the proofs, but the usability of the statements. And here, it looked easy in the proofs. I just had to change the context of my proof. The hard part is improving the completeness here. The fact that if E and F are equal as expressions, then you get a proof in KA. And this is a very nice proof by Kozan and Krob independently, which you have to formalize in ROC in order to use it. Okay. Regarding linear algebra, there are many extensions of linear algebra in the literature. Maybe the most important one being linear algebra with test, which you certainly know very well at POPL', which is an idea by Dexter Kozan. And here I'm in green there because what I did is to put this thing in ROC 10 years ago. Each time in those extensions, decidability is delicate, also completeness is delicate. Sometimes you have decidability but not completeness. But it's difficult, and so far it has not been implemented in ROC. I wish it were, when it is decidable and or complete. And to see why this could be useful, consider this example, which I had presented a long time ago at POPL'. You want to show the equivalence of these two flowchart schemes. And there is a proof in this nice book by Mana, where you move from one to another progressively with some intuitive explanation about why you keep the same semantics. And so they managed to prove the equivalence of those two flowcharts. And 30 years later, Dexter Kozan and Allegra Angus redid this proof using the algebraic technology of CAT. And they managed to write a much more formal proof, much less hand-waving, using 6 pages of CAT computations. This is a nice exercise, but it's really a write-only exercise. If you open the paper, I mean, you can read, it's correct in the end, but it's much easier to write than to read. And what I did is to formalize this algebraic proof in ROC, and here is the proof. It's only three screens long. It's also write-only. You don't really want to read this. But at many places, I use a high-level tactic, CAT or HCAT, to go from one step to another when it is possible to do it automatically. And without this tactic, I would not have been able to formalize Dexter's proof. Because there are places where you save pages somehow. Okay, so this was to show that this technology, which I illustrated on very small examples, is also useful on larger examples. And it's important to have good abstractions, good techniques to deal with the most basic things in order to be able to scale and do more complicated things afterwards. Okay, that was about relations. Now let's move to the second case study, which is about monads. You certainly know monads at POPL. You know that they are useful for effects, algebraic effects. You know some of them. There is a state monad, exception monad, delay monad, and so on. There are many other ones. Lists, multisets. And here in this talk, I'll consider this joke from category theory people. A monad is just a monoid in the monoidal category of endofunctors. It was a joke, because it's abstraction for abstraction, and who cares about abstraction? But I'll take it seriously now, because indeed, this is the right setting to talk about generic results on monads. And for this, I'll need to explain you a bit about monoidal categories. Not too much, be very short. First, categories. You have objects, uppercase letters, morphisms, lowercase letters, composition, which I'll write with a semicolon using the more natural way of thinking, and identity. Should be okay. Monoidal categories, you have the tensor product. Tensor product is somehow the ability to put two morphisms side by side. The formula is not so nice, but it's quite simple. You just take two morphisms, f and f prime, you put them side by side. There are other details about monoidal categories, associators, unitors. For now, we don't care. We do the strict thing. Then comes the painful thing, laws. There are laws in monoidal categories. In fact, there is mostly one law, which is bifunctoriality, which is this formula here, which as a consequence has this other law, exchange. And this is painful. I and j, they look ordered, but they are not, because you see that j here comes first. And here I and j are far away, while here they are close. And it's really hard in terms there to see what is close, what is far away, and so on. In fact, it's a bit like this 15 game. Terms in monoidal categories are like that. You have very basic moves to transform them, but it's really hard to know when you can put things together. Fortunately, people have invented string diagrams, which is the good abstraction for monoidal categories. So here is a string diagram, and to give more intuitions, I will use a small tool. So here I'm in a context where I have three morphisms, F, G, and H, of those types. And maybe I can display F as a string diagram. So this is just a box with two inputs, A and B. This is written here in the type, and one output, B. So inputs are upstairs, outputs are downstairs. I can depict G. This is just a box with one input, one output. I can depict H, a box with two inputs, two outputs, and somehow it swaps the two strings. Then I can do compositions. I can compose F with G. This is vertical composition. Semicolon is vertical composition. Okay. So here you should look at this term, which I'm writing, and see how it relates to the picture. I can compose them horizontally with a tensor product, which is written with a small dot. Okay. So here I get a box with three inputs and two outputs. And so once I know I can do this, I can do combinations, right? Since I end up with B and C here, I can plug in G again. Not G. H, thank you. Okay. And here maybe I want to plug G again on this, in this place, but G alone is not enough. Because here I must plug a box which takes some CB, not just B. And in order to do this, I can use the identity here. And the identity, I can write it either as ID or as the object. It depends what you want to emphasize. Okay? So these are string diagrams. Why are they useful? They are nice, but why are they useful? They are useful because they make it possible to abstract away those painful laws which we were seeing before. So here is just I compose tensor J, okay? So two small boxes. And the exchange law from my slide before, this one, the second one, actually is the fact that Ij, I can see it in other ways. I can see it in this way. This is giving priority to I. I first, then J. Another way to depict it, say I can be up, can go up, and J can go down. Okay, and I can see this diagram as I with the identity composed with J. Of course, I can also do the converse, right? I can put J first. And all this law is saying, the second one, is this, that you can slightly slide the morphisms in your picture. Similarly, for exchange, for bifactoriality. So here, this is written as f prime composed with gg prime, but I can decide to write it as a single horizontal composition of two vertical composites. And this is really bifactoriality. But I have other choices. Maybe I can put f here in the middle. So here this is a composition of vertical composition of three things, and many other choices. So this is why string diagrams are useful. In fact, there is this completeness theorem saying that two expressions in monoidal categories are equivalent if and only if they denote the same string diagram. So this theorem really says that string diagrams is a good abstraction for working in monoidal categories. This is how you want to think, and this is also how you want to implement things in a proof assistant. You want to reason automatically about these equations. In fact, when you have two expressions like that, you have a way to decide that they are equal or not, an algorithmic way, and this should be implemented in a proof assistant. You don't want to solve this by hand in the proof assistant. Okay. Now let's go back to monads. Monads, which I've told you, are just monoids. So I should explain you what is a monoid. A monoid is an object with two morphisms, mu and eta. Mu is the multiplication, eta is the unit. And now if you think concrete a little bit, if you go back to monads in sets, you should think of objects as functors, tensor as functor composition, and arrows as natural transformations. And maybe the monad M is a multiset monad. Multiplication here is take a multiset of multisets and flatten it into a multiset, and so on. But here it's abstract. You don't really need those intuitions. You just have this morphisms. Now, I've told you we should use string diagrams. What are the string diagrams for those two morphisms? Well, we can depict them in this way. A box with 2 inputs and 1 output, and a box with 0 input and 1 output. This morphism should satisfy a few laws. I mean, it's a monoid, it should be associative. And the standard laws are those ones. Painful to read. Not too long, but... You can draw diagrams for them, slightly better. Maybe here this is really the diagram for associativity. This is where you understand that this is associativity. You have 2 ways of going from M3 to M, and those 2 ways should be equal. But what's the good way of thinking of this is the string diagrammatic way. Here are the diagrams. That's much nicer. So here, you collapse 2 things into one on the left, then on the right, and here same thing, first on the right, then on the left. This is really associativity. Here I've just written the diagrams for the 2 terms, and same thing on the right. Okay. Now comes the theorem. I want to compose monads. You certainly want to compose monads. You want to combine effects. You want non-determinism with state, non-determinism with exceptions, with probabilities, and so on. And for this, if you want to stick to algebraic effects, you need to compose monads. In my setting, this is just composing monoids. And you certainly know that there are conditions, very much like in the first example of the talk. You need distributive laws. Okay. A distributive law is just a morphism from NM to Mn, which you can depict using this small box, which allows you to cross strings. And if you are given such a box, you can easily construct a multiplication, say, on Mn. This is this diagram. This is a diagram from Mn square to Mn, which I obtained by swapping the 2 people in the middle and then multiplying on both sides. If you really insist, I can give you a term for it. But I don't care about the term, in fact. Now, distributive law of monads, they should satisfy some law, some coherence law. So the exchange should play well with multiplication and unit. Here are the laws. I mean, 2 of them, I forgot the unit, and I'll do in the rest of the talk. You can draw diagrams again, which are not so illuminating. Or you can draw the string diagrams, and there you start understanding. What you need is that the fork, the multiplication, should be able to go under the cross, the exchange here, and go there. On one side, and also on the other side with the other fork. Okay, so let's get back to the theorem. I want to prove it, so I define my new multiplication, this strange mu here, and I need to show associativity among the other things. Here is a diagrammatic proof. It's correct, it's awful. Still, we can get some grasp on it. Let's abstract a little bit. I remove irrelevant details. Here, if you look carefully, you'll see that you use associativity of the 2 monads here and there. Those are squares. And there are also 2 pentagons here, where you use the interaction between the exchange law, the distributive law, and the monads. And all other squares and triangles, they are just exchanged by functoriality, which in the special case of monad is naturality of concrete monads. So all those, I think there are 13 steps here. They are painful steps which you don't really want to see, in fact. What you want to do is a string diagrammatic proof, and it will look like that. I will not discuss it right now because actually what I want is a string diagrammatic proof in rock. And this is what I'll do now. So where is it? Here. Here's the statement. I have a monoidal category, two objects which are monoids. So here is the multiplication of my monoid, its associativity. Here is multiplication of the other monoid, associativity. Then there is the distributive law, X, and its two coherent axioms. I construct the composite multiplication here. So here I need the term. This is the term that was on my slide up here. This term. And I proceed to proving associativity of this composite multiplication. What can I do? I'll just copy-paste the goal into this wonderful tool, which is there, blank. I copy-paste. And here, what do I get? I get the four equations, the four hypotheses, so associativity of the two monads and coherence laws, and my current goal. I should show the equality between those two string diagrams. Where here, the orange boxes, they are the composite multiplication. I can open those boxes. Yep. And now I can start working. What do I want to do? Given the laws which I have here, maybe this fork is willing to go down. So I can select this pattern. It matches one of my hypotheses, and thus I can replace it with the right-hand side. Same thing on the right-hand side. Okay, I see a pattern, it matches one of my hypotheses, I rewrite using it. I'm not yet done because you see that the monads are not in the same directions, the turquoise and violet monads. So I should still reorder those. And same thing, let's do it nice on the right. Great, I'm done, I've obtained the same diagrams. But for now, this is just some OCaml code with my mouse on the computer and so on. I want something formal. And now there is a button, which is a capital E, I think, which tells me rock script copied to clipboard, which means I can go back to my rock proof and copy it. Here is the proof. So it's short. It's not extremely short, but it's short, it's concise. What is happening? Basically, the proof is just 4 rewriting steps, right? They are there, the 4 of them. Yes, you see. Each time, I do a transitivity step where I make it explicit that there is some match. Here, this is the left-hand side of NX. So I do a transitivity step to make this subterm explicit. Then I use an automation tactic to solve the goal. Okay, the two terms, the previous one and the one where the match is explicit, they are equal. They have the same string diagram. I can solve this automatically. And then I can do the rewrite as expected. And I continue. I want to do the second rewriting step, same strategy. I make it explicit that there is a pattern. To make this explicit, I use automatically, I use the MCAT tactic, and then I rewrite, and so on. And in the end, I get 2 expressions which have the same diagram, so I can prove them equal using MCAT. and I'm done. Okay. So here's the proof in rock. Is it convincing? I hope so. Well, if you understand string diagrams, it should be convincing. Is it concise? It's concise. It could be more concise. For instance, I could hope to replace those transitivity rewrite steps by a single call to an M rewrite tactic, which doesn't exist, which is rewriting modulo string diagrams somehow. This is feasible. I'm willing to code it. But before coding it, is this proof better than the previous one? This, I don't know. It's more concise, but if you just read it, you get less information. So maybe, in fact, the previous proof is slightly better. For me, both of them are robust. If you slightly change the statement, which you cannot really in this example, but both of them would be okay, because this one, you would expect mrewrite to take care of the work, and this one, you could hope to modify manually the terms. Okay. To show you that it's convincing, I could do 3 monads. I won't because I don't have time, but it's a very nice exercise to do. And you'll discover, doing the exercise, that it's not obvious which laws you need. Certainly, you need 3 distributive laws, but in fact, you need a bit more, and this you discover when you do the exercise. And this is nice. Under the hood, maybe you have noticed that there was this strange symbols, prime here on equiv, and double semicolon. And these are not typos. If I go back here, you see them here, prime, 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 double semicolon, double semicolon, double semicolon, blah, 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 blah. In fact, those are notations which make it possible to elude all questions about associators and unitors, which you have to take care about, which are painful to do. In fact, even in this ugly proof, they are not there. This is a proof in strict monoidal categories. But strict monoidal categories, you cannot formalize them, really. You will end up having equalities anyway, so in the end, you will have the same amount of work to do than to formalize arbitrary monoidal categories. And here, it really works because I do have this setup to infer automatically what are called MacLane coherence morphisms. So to show you here I cannot write a single semicolon because it does not type check. Because here you have 2 transfer expressions in the middle which are not associated in the same way. So for it to work here, in the middle, you need to add something, associators. And those are really painful to write explicitly, so you want to infer them automatically. And I do here. I do using those notations, using some powerful mechanisms. And this you can do safely because there is a nice theorem, MacLane's coherence theorem, which says that any 2 morphisms, any 2 MacLane morphisms with the same sources and targets are equal. So you can infer them automatically because you don't care about which one is chosen. And this is really crucial. Okay. Now, to sum up on the two case studies, what made it possible? First of all, nice theories and abstractions. So linear algebra on one side, string diagrams on the other side. In both cases, those are quite old abstractions. Second, you need decision procedures. And to go to proof assistance, you need certified decision procedures. And here, what I use in a very strong way is reflection, the ability to compute within the proof assistant in a certified way in order to get proof. I use it at many times, not only for the three tactics which we have seen, but also for this MacLane morphism inference. Here I do this by reflection again. And lastly, you need powerful notation systems. It wouldn't work without those notation setup. The tool is in strict categories. I don't care in the tool, when I program in OCaml, about associators and units. The ROC is with associators. And I can communicate between the tool and ROC because I managed to set up a nice notation system. Otherwise, I would not be able to communicate. So this is really crucial. There are other theories which can be automated, which are automated. I list a few of them here. And all of them help us writing better proofs, I think. And in this list, all of them are rather robust. And they are robust because in each case you have clear specifications and you have complete algorithms. I insist on complete algorithms because if you have a semi-decision procedure for something, it cannot be robust. It will work in one case, you will try to adapt it to some other case, it will fail or not terminate, and you won't know why. It's not problematic that it fails. But it's problematic that you don't know why it fails. And this is really important. This is what makes things robust. I've also not discussed other important automation tools. There is generalized rewriting, where there is quite some work in various communities. And even more importantly for me in this work, even though I didn't show it, there is a support for hierarchies. You need to set up hierarchies of structures and to set up concise notations. This I explained. And for this, you have to do a lot of work. And for now, this is rather ad hoc work. And here, I think there is a big room for research within POPL, taking inspiration from programming languages to provide a structured way to do notations, to do structure inference, and so on. And I'll stop here.
Do we have questions in the audience?
Hi, thanks for the very nice talk. I was wondering how widely applicable the whole rewriting modulo sum matching would be. Have the same very similar pain points with the equational theory or substitution calculus, where you also want to apply lemmas up to that equational theory, and it's also extremely painful, and I'm really wanting whatever mrewrite is doing.
Should stay here. I would say the approach is quite generic. At first, you need a decision tactic for the equivalence. And this has to be certified. Then you need something to detect matches. Something which is able to, given a term, see if there is a way to write another term with an explicit match. And this, of course, depends on the theory. If you just do associativity and commutativity of some symbols, there are algorithms. If you do string diagrams, there is an algorithm. If you do linear algebra like I did in the beginning, there is no algorithm. You cannot rewrite, you cannot find a match modulo linear algebra axioms. There you could do heuristics, but then you get the problem that it won't be as robust as you might hope. But the overall approach is quite generic. Then it depends on each theory, whether you can find a matching algorithm.
Thank you. Okay. Thank you for the talk. So you had this nice tool that you wrote in OCaml to fiddle around with the string diagrams, and then at the end you generated a rock proof. Did you ever think about integrating that? So I think in the competitor, so in Lean, they have all kinds of fancy ways where you can display proof states in some nice way. And also in Rock there's Electron. Did you ever look into that?
So to integrate the thing, the way I proceeded makes it partly easy to integrate. The standalone tool is really standalone. To communicate with it, all you need is to be able to write and read in a text syntax. So then you have to go to your proof assistant and to set up a framework to work nicely at this abstraction level. So for instance, you need the MCAT tactic. So if you can redo the MCAT tactic in another proof assistant, you're on good track. Then you also need to do the notation system. You need to be able to infer McLean morphisms nicely. If you can do this, then you're fine and you can swap ROC for another proof assistant.
Yeah, but that was not entirely my question. My question was, did you ever think about integrating this tool in the proof assistant so that while executing this proof script, you would actually see the string diagrams on the right in your proof state, and you could actually change the string diagrams there and would immediately insert like the corresponding tactics?
You could. That would be really easy, except I don't know how to do it because you have to go into the internals of the proof assistant. And not only this, but also the internals of the interaction of the proof assistant with the text editor, which I don't really know how to do. This is why I delegate to me doing some copy-paste. But right now, you are almost there, right? If you're in this proof, I didn't cheat. Here, maybe you can do some manual steps here. Okay, imagine the first steps, I did them manually. I can, at any point, copy-paste the goal, go to the tool, and now what I see is the current state of the goal. And I can resume from there. So, and it's really important, indeed, that there is a small step correspondence between what I can do in the proof assistant and what I can do in the external tool.
So that already works by that you can just copy-paste this proof state. So that
yeah.
I had a question regarding mRewrite again.
Yeah.
What happens if you have multiple matches, multiple ways to rewrite the equation you want to rewrite?
Yeah. Maybe this is why I don't want to, I didn't implement it yet, or maybe I won't implement it. Here, even in the tool, I didn't do it. Here, I have this idea of selecting a match and finding the hypothesis that match, which is automatic. It would make sense to do this, right? Click on this hypothesis and have displayed in the main term here all matches, and then select one. This is feasible here in the tool, and this starts being painful in the proof assistant because then you need a way to designate or to enumerate all potential solutions and say, well, I want the fourth one. But if you start using numbers, then you are not robust anymore.
Yes, hi. Thank you for the talk. It was great. So I have a follow-up question on the previous question. Now here in the tool, you're selecting the term that you want to rewrite.
Yeah.
But the tactic that you produce is just a rewrite. How does that select what term you want to rewrite on the ROC side?
Here, what I do, let's say, where am I? Maybe suppose I want to, I do this thing. Okay. Here I select a box, and when I select a box, I can extract with E a term for this graph where this box is highlighted. Here you see this term, and there is a box here which corresponds to this subterm. So this is a computation which is easy to do on the diagram. And now this term, which I can easily extract, is the one which is given back here in the proof as a transitivity step. What happens? Here, I don't know if it is this one, maybe it is. This term here is the one I could compute just by looking at this picture with an isolated box. And this is how how it works. If I want to do a rewrite step in the tool, I translate it back to a transitivity step through the explicit term, then a rewrite.
Does your transitivity then ensure that there is only one match?
There can only be one, because the match is given with these small boxes. And actually, so you might decide to put two of them. And this is what I do in the displayed proof here. This is a slightly reworked proof here, which is displayed. This is not produced by the tool. This is adapted. Here, the first one is produced by the tool. The second one, I realized that I can do two rewrite steps in parallel. So instead of doing it like before, I make it obvious that there are two matches, and then I can do the two rewrites. So there is a lot of flexibility here. Basically, you can do whatever you want. Yeah.
So you've explained how there's various principles that help humans create convincing proofs. Do these principles also apply for LLMs creating the proof scripts?
I don't know. Maybe we should ask to ChatGPT.
Let me remind you that the talk is mirrored in the other room, so we have another question, maybe from one other room. You can also ask questions from Discord, and here is one I'm going to read. In your examples, medium-scale automation builds on nice abstractions for the problem domain that come from decades of research. How would you try to automate more in progress theory?
That's a fair question. I mean, I think we should start from the basic and automate more and more until the point where we understand. There is this challenge, for instance. Right now, when I did this work, it's still quite ad hoc. I use some knowledge, some tricks in the proof assistant in order to be able to implement notations, to implement structure inference, and so on. And this is still ad hoc. So, and even on small examples or long-standing examples, say, like that, it's not that easy to make it right. So I think first we need tools, and this is where I call for the PL community, tools to be able to do this in a more systematic way, even on simple case studies, like the ones I've discussed. And I think only then we can hope to automate and to provide good abstractions for more recent, or more complicated often, theories.
Maybe a last question?
Hello. So does this nice proof where you have 4 rewriting steps that the user has to find by hand, but if I want more automation, is there hope to automate the whole thing using maybe equality saturation or something like that?
You could imagine, yeah, you could imagine to have a kind of congruence tactic modulo string diagrams. I don't know if theoretically this has been studied, if this is really decidable, but maybe some fragments of it are. Here, also, you see that when you write it in this way, you can be more aggressive. Actually, the proof, if you generalize to many monads, you always have to let those forks go down and then reassociate. This, once you have an M-rewrite tactic, you could imagine to say, okay, rewrite as much as possible modulo the theory, the exchange of monads and exchange and distributive laws, get to a normal form, then do associativity and conclude. This is feasible. In this example, it won't work because if you want to compose, say, 3 monads, you need one more hypothesis, which is not easy to orient. So it wouldn't work by just normal forms, but still you would get to normal forms where you just have only this law to apply, so that's already some progress. And then in general, can you do equality saturation and so on? Possibly. that would be super nice to be studied.
So, one of the key ingredients you said you had was that you're using reflection. You said reflection is necessary for this to work. Why is reflection better than creating proof terms?
Because proof terms would be huge, if ever you can write them explicitly.
Maybe they can be in memory, right?
Sorry?
You can have them in memory and check them in memory. It's still going to be faster than checking the entire decision procedure.
Let me go back to an example quite at the beginning. Here I produce proofs in Ka. Ka is an axiomatic system, so a proof is just a tree. It would make sense to, have an oracle produce the explicit proof and type check it. Problem is, this proof, you don't really know how to produce it effectively. The theorem is constructive, so there is an algorithm, but it would produce a proof which is huge, but even more than huge. In fact, here it's much better to not produce the proof, to just run the algorithm that checks the equivalence of the two expressions, and know that when the algorithm says yes, indeed there exists a proof. The problem is p-space complete. We do small instances, so it's not a problem of being p-space. But the computation takes some time, it's okay. But the proof, the Ka proof it would produce would be enormous. And you would not be able even to just store it, I would say.
Thanks.
Okay, I think we should stop here, so in order to get to the coffee break. So let's thank our speaker again.
Merci.
So now you can go to coffee break just...
Microphone 2. Hello, everyone. Is it working? Yes. Hello, everyone. Welcome to our first non-keynote session on functional programming. Sorry we're starting a bit late, so everything will be roughly 15 minutes shifted. First, we're going to have Samson talking to us about domain theoretic semantics for functional logic programming. Yeah, feel free to start.
Thank you. Okay. Wonderful. Thanks so much. Good morning. So our paper, we present a functional logic programming language and do some denotational semantics on it and various analysis of it. So to first provide a common ground of what we mean by functional logic programming, I thought we'd just go through a very simple example, quite a well-known example. So we've got this program here, last, which hopefully it's quite clear, computes the last element of a given list. There is no recursion. Instead, we declare two variables, x's and x, and we take our input y's and equate it with the concatenation of x's and the singleton x. And then if that is successful, we can return x to obtain the last element of the list. So this example quite clearly demonstrates what we're interested in. First and foremost, it is a functional programming language which we extend with features inspired from logic programming, namely non-determinism, logical variables, and equational constraints. Non-determinism being necessary because there could be more than one solution, or you might have to consider a bunch of solutions to continue evaluating. So FLP itself has quite a long and rich history. We've got this review article here, which just provides a general survey of it. I think it was published in 2010, so many years ago. Unfortunately, there hasn't been an adequate and fully abstract denotational semantic for a language which supports the three main constructs that we're considering. So regarding what we present, we first introduce a typed call calculus based on call by push value. And we're able to do this because we understand the effects we're adding on top of our functional language as algebraic effects. So we can take full advantage of call by push value to do this. We present an abstract machine based upon Staten's algebraic theory, which is it's an algebraic theory from an algebraic presentation for predicate logic. It's the title of the paper. We then examine domain theoretic denotational semantics, in particular using the lower power domain. And then we examine a specific model which we show to be adequate and fully abstract for the abstract machine. However, it's only relative to a termination insensitive notion of program equivalence. So we can have two programs, and if you just take the same program, then once it's finished evaluating, you just run a program which diverges. Unfortunately, our model will say that these are the same program, and obviously this is a shortcoming. Regarding how we can actually fix this, we examine what is necessary for a domain theoretic model to be able to distinguish failure in order to be able to model this termination property that we seem to be interested in. So regarding the types of the language, we've got all the usual stuff. It's called by push value, so we make a distinction between value types and computation types. Value types not having an underline underneath them. So you can, in call by push value, you can always go between value types and computation types via funcs to go from a value to a computation, and, returners to go from a value to a computation, and funcs to go in the other direction. And we also single out a collection of what we call first order types. Now, if you have a quick look at them, you can see that these are exactly the value types which are not funcs, or don't contain a func anywhere in the syntax. And so what this means is they were never at any point a computation. So here's the call calculus. So for instance, if you want to make a natural number, there are only three laws that you can use to do this. It's either going to be a variable, zero, or successor. And so if you actually want to do something with this, with a natural, you'll first have to return it, to turn it into a computation, and then you can proceed from there using bind and, for instance, if zero, if you so desire. We've also got fix here, quite unusual. So variables in call by push values always refer to values. So in order to define something like fix, you would have to use a func on the computation that you are trying to define recursively. So we've also got typing judgments for the effects that we're interested in. At every computation type C, we have a judgment for failure. We're able to combine two computations to give non-deterministic choice. And we can also quantify it over a variable in order to define exists and equate two values and then proceed evaluating a computation. Note that we use sigma in the judgments of exists and equate. The idea is that we can only quantify over first-order values, and the reason we want to do this is because these first-order values have a very nice inductive structure that we can use in the evaluation strategy when we actually want to run these programs. So regarding the abstract machine, we take the CK machine, which just consists of the computation and the stack on this diagram. And we append a context gamma, which will contain our logical variables. And the idea is that as you evaluate a computation, you accumulate these variables throughout the execution. So what this means is that if you start with a closed computation M, as it evaluates, it might become open. It will always be closed with respect to gamma, but as a term on itself, it might be open. In order to perform narrowing, we use what we call a weak head narrowing strategy, which is is inspired from what is known in the literature as needed narrowing. So here is a short example, or a short collection of our effect-free transitions. If you want to evaluate something which binds a computation, you first push the continuation of the stack, evaluate M. If M doesn't diverge, also doesn't perform any effects, then it will reduce to a computation or to a basic machine where the computation is return V. You then proceed by popping the continuation of the stack and doing the appropriate substitution. We've also got if0 here. It's very clear what to do when the value that you've got in your if0 is 0 or successor. But as I said earlier, the computation might become open. And so it could be the case that you are doing if0 on a logical variable contained in the context. And it's not exactly very clear what we should do then. Intuitively, we want to consider two cases, the only other two cases for a natural number that is not a variable, namely it being 0 or successor. But as it is, our basic machine can't handle this sort of non-deterministic behavior. So we extend basic machine to that of a configuration. Configuration itself will either be fail, some basic machine, or a choice of two other configurations. So you can imagine it's some sort of tree structure where the leaves are either failure or basic machines that are still evaluating. And then we can lift the effects that we have in our computations in order to define the transition relation. We just lift it to the level of configurations. So failure in a computation becomes failure at the level of configurations, and the same for choice. To deal with exists, so this is a quite clear example or demonstration of how a computation can become open. You simply push the logical variable that you're quantifying over into the context. So in order to deal with unification, we use the very well-known idea of a most general unifier. So we're able to do this because all of the values that we equate are first order, so the algorithm that does exist applies. And the intuitive idea is that you find the least, the formal definition is it is a substitution which will syntactically equate V and W. It being most general means that if you have any other substitution which equates these two values syntactically, it factors through the original substitution. And once you find the most general unifier, you apply it globally, both to the computation and the stack, and you also update your context of logical variables. Now, obviously, there could be cases where there is no most general unifier, for instance, if you equate 0 and 1, and in that case, we just return fail at a configuration and stop evaluating. So regarding this example, this is very motivating for the strategy we use of weak head narrowing. So we've introduced configurations, and now we're able to do something like this. We say that an abstract machine is blocked on a logical variable x if you cannot continue evaluating without knowing more information about x. And in this case, we continue evaluating by introducing the least amount of information we need least amount of information we know about x, namely it being 0 or successor. So you return a choice, x replaced with 0, removed from the context as well, and then x replaced with some fresh logical variable n, and x substitutes for successor event, or the other way around, rather. And so, going back to this problematic example, we can continue evaluating like this, and it's obvious what to do now with the if0. So just a very short example, execution of a program. So hopefully it's quite clear that this should give you some positive natural number, and you can follow through and check that each one is indeed correct. So we get, in the end, we get return successor of 0 or successor of some natural number n. And a simpler program which does the exact same thing is to introduce two logical variables n and m such that n is the successor of m, and the transitive closure of this will give you successor of n as the resulting computation. So because all of our first order values have an inductive structure, we're able to apply the exact same idea to them. So for example, with lists, you replace x with nil, or you conjure two fresh logical variables and consider cons of them. And we also have a completeness result. So results is something I will define later, but intuitively it's just, the final set of values you get at the end of running your program. And we say that if you have any value of the appropriate type, then substituting x with that value will never give more results than quantifying over a logical variable. So regarding the denotational semantics now, we have recursion, so we're going to need complete partial orders. Namely, all our value types will be complete partial orders. The first order value types will be discrete posets, discrete partial orders, which are trivially complete partial orders. And the denotation of computation types will be complete pointed partial orders, which means that they will have a least element. Now we note that in call by push value, effects only occur at computation type. So we just need to add some suitable algebraic structure to the computation types. So we have non-determinism, which means that we are going to need some sort of join semilattice structure. If we have two elements in this domain, we should be able to return their join, which is the non-deterministic choice. But we also have unbounded non-determinism. Because we quantify over naturals, for instance, which is an infinite data structure, has infinitely many values, you can quite easily, especially in the presence of recursion, construct an example where we do an unbounded amount of non-determinism. As such, it's not enough just to have a joined semilattice structure. We actually require a countably complete joined semilattice structure, which means not only can I take joins of finite sets, I can take joins of potentially countable sets. And so the question is, how do we combine these algebraic structures? One might think you can just use the power set in order to deal with this, but unfortunately it completely destroys the complete partial order structure you have on your terms. So instead, we use power domains, which is the domain theoretic analog of the ordinary power set, and it preserves the CPO structure that we're interested in. So regarding the choice of power domains that we have, the most simple one is the Plotkin power domain. So we have this join symbol, which is a function of arity 2, and we require these algebraic equations, namely commutativity, associativity, idempotence. We've also got this symbol epsilon, which we use for failure, no results. And we require it to be a unit of the join. You can then consider more equations on top of these. For instance, if we add this equation here, x approximates x join y, quantified over all y, of course. Then we get the lower power domain, or Hoare power domain, where non-determinism should be considered angelic. That is to say, more non-determinism gives me more information. I can obviously do something quite similar, where instead I say x join y approximates x. And in this case, we get demonic non-determinism, where more non-determinism is bad. It's interesting to see how the unit epsilon interacts with these equations. Notably, in the lower power domain, you immediately get that epsilon and bottom being the least element in your CPO structure, are the same thing. We also note that neither the Plotkin power domain nor the Smith power domain actually support unbounded non-determinism, which we need. As such, we are forced to choose the lower power domain. So regarding its construction, we take a complete partial order D, and we say that any subset S is Scott closed if it's a lower set and admissible. So a lower set meaning it's closed downwards according to your approximation relation, and admissible meaning it's closed under directed joins. Any directed set contained in S, it should also be the case that S contains its least upper bound. Then you may form the lower power domain as the complete pointed partial order of Scott closed subsets of D, ordered by ordinary subset inclusion, where we take the empty set, which is a Scott closed set, as the least element. From this, we very clearly demonstrate how you can construct a denotation for every term in the language. It's quite involved, I won't go into it. But notably, we end up where the denotation of fail is the same thing as the denotation of any program which diverges. Again, this was forced by the lower power domain. So modeling the machine in order to assess how good our model is, we take a configuration, and you can consider the results of this configuration. So this triangle here, this thing here means that this basic machine on the left is a leaf of the configuration. We're interested in all the ones that have finished evaluating. V can be open, closed with respect to gamma, so the context gamma. So what we do is we consider all substitutions of the variables in gamma which close V, and that will give you all your results. You can then extend this to a closed program which does return things. We only do this for programs of type FA. And we start with the basic machine, no variables, no stack. And you consider all configurations that you go through as you evaluate this program. And from that, we can accumulate all the results in each configuration. So for example, it's quite clear that this program here should give you all the natural numbers as its results. We can then define a relation between terms where we consider all ground context, that is a context such that when you substitute m in, its type will be of f sigma, sigma again being a first order value, and we say m approximates n, observationally approximates n, if the results of this, if this equation holds. Note that the relation is inherently termination insensitive because in the presence of non-determinism, absence of a value does not imply diverging behavior, which you would ordinarily have in the case of something like PCF. So termination sensitivity is something you have to build on top of this relation. So regarding how effective our model is, we have a complete equivalence between the observational approximation relation between terms and the approximation relation in our model. How we prove this, very standard. To prove the backwards direction known as adequacy, we introduce two logical relations. Two because we're in call by push values, so you need one for values, you need one for computations. And then we prove, you simply, well, it's not that simple, it's quite long. You prove by induction this following lemma, whose intuitive meaning is that the meaning of terms preserves the logical relation. It's very well known in the literature. For the forwards direction, our proof is quite elegant. It's made much simpler by the fact that we can demonstrate all compact elements in the model are definable by some term in the language. So regarding how well we can actually can we actually construct a model that is termination insensitive on top of what we already have? And so we can say a model is failure discerning if the denotation of failure and diverge are distinct. And we argue that if it's not impossible, it is at least very difficult to construct a domain theoretic model which is failure discerning, subject to a small set of what we argue to be very reasonable equations. So our first argument, if you consider this equation here, dead end, so I have some computation m. If I then bind it to a variable, and then proceed to do a computation which always fails, we want this to be the same thing as failure. And there's a very obvious practical reason for why you would want this to be the case. If you're actually going to go and implement this language, you'd want to do something like this. It becomes problematic, however, when m is a computation which diverges, because you immediately obtain that diverge is fail. But perhaps you might say this is the only exception to the rule. And then we say, well, in response to that, we have this second argument. So we have these equations here. We require failure to be a unit of non-deterministic choice. Now we require, if you quantify over a program which always fails, this should fail. This is even more reasonable than this one, because any practical implementation really should do this. And then finally we have this equation here which says if I quantify over a variable and then run m, it should be the same thing as a non-deterministic choice where I consider 0 and then quantify over all the natural numbers incremented by 1. If in addition to that you have that the denotation of exists, which I've labeled, use this variable here, if that is also continuous in regards to domain theory, then we are able to immediately conclude that your model conflates failure and divergence. And so as such, it seems to be quite a difficult problem to obtain a model which does distinguish these two terms. Thank you for listening. My references.
any questions? Anyone who's ready, give a question.
Hi, thanks for a very interesting talk. So I just wonder, have you considered a variation on your language where the choice is not unordered, but it's ordered, and then have a construct that can take a bunch of choices and turn them into a list?
Sorry, what was that last bit again?
And add a construct that takes choices and turns them into a list. So you can reify the...
Yes. We did consider this, and it would just be a fundamentally different model, I think. At least you'd have to drop some of these equations, namely, as you say, the commutativity of non-deterministic choice. But then looking at the power domains that we're interested in using for the denotational semantics, it's required that choice is commutative, so our work doesn't really apply in this case.
Pity.
Hello, I'm Joseph Zulo from Purdue University. On this slide, we have that, so X is universally quantified, right? So we have that bottom join epsilon is by left unit, bottom by the right unit, or the other way, by right unit, bottom by left unit epsilon. So I don't see how they could ever be distinguished, assuming that bottom and epsilon are both units of join.
Right. So this, if you do plug in bottom here, you will get bottom. But then what you say about considering the other way around?
So if you use the right unit, then X is bottom. If you use the left unit law, X is epsilon. So equals bottom equals epsilon, no?
I don't think so. So you're saying if we use commutativity, you would just get bottom again?
Yes, because commutativity combined with the fact, I mean, I don't think you even need commutativity. Monoid units are unique, no?
Mm-hmm. Yep.
So I don't see how bottom and epsilon could ever be distinguished.
I think choice doesn't have to be strict. So choice doesn't have to be strict.
What does that mean?
So you don't need that bottom choose anything is bottom.
So bottom is not a unit of...
Not necessarily.
Makes
If it's a unit, they're unique, they're the same. And that's characteristic of the lower power domain.
Okay, I see.
In other power domains, that's not true.
Okay.
I think we've got one more question up here somewhere. Yes.
Okay, thank you for the talk. So I was wondering if you could justify the dead end thing a bit more, because from a traditional programming perspective, this is not a reasonable axiom, right? Like if M have some effects, including divergence, then I definitely don't want you to start optimizing away my stuff. Is this like a restriction of the language you're considering? Is this something about FLP generally?
It is just one of our arguments for why it's quite hard to discern failure. It is, in some regards, it can be seen as quite unreasonable as we've identified, but then we have this other argument instead.
Oh, so is it either one? Because I thought it was a combination of all of these, if you obey all of these equations. Because I would
Oh, sorry. This is one argument on its own. If you have this, you conflate failure and divergence. If that's not true, maybe you still have this, and same result.
If I can ask a quick qualifier, what justifies the existential one? Are all of your first order types inhabited?
Yes.
Okay, well, that does explain it.
Hi, thanks for your talk. I just have a I have a question and a comment. The question, I suppose, is, do you see this work generalizing to like a constraint programming scenario as opposed to just logic? So sort of broaden the set of constraints you allow to more than just logical. Do you see that generalizing to that scenario?
Do you mean specifically the equate judgment?
Yeah, yeah.
What would you mean exactly?
So for example, broaden that to allow maybe finite domain constraints on integers?
Sorry?
So allow, for example, to like broaden it to like finite domain constraints on integers, for example.
I don't think I'm familiar with this, unfortunately, but I'd love to chat after.
And a comment, I suppose, with this slide in particular is that in my work on search heuristics for constrained programming, we actually, like failure is not actually a unit of a non-determinism, because you might make decisions in the heuristic based on how many times you fail. And so I'm just questioning whether this is indeed like a sort of reasonable thing to want.
Yeah, certainly. But for an extensional model, one might argue this should hold. So perhaps you'd need some sort of intentionality to accommodate for this.
Right, thank you.
Let's thank our speaker, and we'll move on to the next talk. So next we'll have Michael telling us about handling scope checks. Yeah, please start.
Hi, I'm Michael, and I'm going to be telling you about handling scope checks. So this is joint work with Ning, Oleg, and Jeremy. I'm going to start by setting the scene. So this work is grounded in the context of MacOCaml, which is a project that aims to add compile-time metaprogramming to OCaml. When you're adding metaprogramming to a system with effects, like OCaml has, you have to be worried about scope extrusion. I've put up the definition here. It's the unintended and undesirable consequence of the interaction between metaprogramming and effects, but we'll see concrete examples of that later. I don't expect you to understand what it is right off the bat. There are various ways of solving scope extrusion. It's a well-studied problem. And the first two of these, refined environment classifiers and closed types, they are static prevention techniques, and the last of these is MetaOCaml check. So MetaOCaml is a runtime metaprogramming system for OCaml that's a dynamic check. And we knew that we wanted a dynamic check because we didn't want to mess around with the OCaml type system. And we could have picked this and just taken it off the shelf, and that would have been fine, I guess. But instead, I had to ask a question. And the question I asked was, what's a dynamic scope extrusion check? And are there different types of dynamic checks? And are there trade-offs between these different checks? Do different checks even solve the same problem? And are these checks designed with effect handlers in mind, or just, state and exceptions? And asking these questions led to some answers. For example, we developed a theoretical framework for scope extrusion, which has typed effect handlers at both compile and runtime. We use this framework to facilitate comparison of different types of scope extrusion checks. Turns out that they don't all solve the same problem. They're similar but different, and we make that precise. They also didn't accommodate effect handlers, so we designed a scope extrusion check that did. And we showed that they can work well with static type systems, even though that's not our main focus. These are the contributions to the paper. Before you get your bingo cards out, I'm not going to be talking about all of these. Instead, I'm going to be focusing on just 3 of these. But before I asked any of these questions, I had a much simpler question to contend with, which is, what's metaprogramming? And that's not a question I have time to answer today, but I'm going to ask a different question, which is, what's MacOCaml-style metaprogramming? And for those of you who are familiar with the literature, this is 2-stage, homogeneous, compile-time metaprogramming, and that question I can answer today. So metaprogramming is the act of writing code that writes code, and if you've ever written a C macro, or a C++ template, or a Rust macro, you've done some metaprogramming. Our model for metaprogramming is programs that build ASTs. So here's a language in which you can do metaprogramming, or here's the syntax of a language in which you can do metaprogramming. We're going to assume it has the sort of obvious semantics. And it's important to note that this model of metaprogramming as AST building isn't new. So that's a paper you can look at if you're interested. You can also read off the programming language in which we generate code. The programming language of the code we generate just by looking at the ASTs. It's also a slight simplification of the language that we present in the paper. We also have a formal parameter constructor So what we mean by this is that the AST of the identity function looks like that, rather than lambda var alpha. It's just to keep things, it's just to keep the type system simple. We don't really have to worry about it. But here's our programming language in which we can do metaprogramming or AST building. So we've got our programming language, we can write some programs. We can write, for example, the AST of the identity function, or we can write the program that actually computes, that does some computation. So this is a function application. On the left-hand side, we have a function that takes an argument and constructs the AST of that argument plus 0 that we apply to the AST of 1. So we can run it and get the AST of 1 plus 0. And this is sort of what happens at compile time. So compile time evaluation produces compile time normal forms, and these compile time normal forms are ASTs or runtime terms. They are ASTs or runtime terms, so we can move it into the runtime world where it's 1 plus 0. We can run it, and we can get 1. And that's just the regular runtime evaluation that you're familiar with. So that forms our model. We start off with a compile time term, which manipulates ASTs. We run it to get the AST of a runtime term. We then bring it into the runtime world and run it again, and then we get our runtime normal form. So that's our language in which we can do AST building, but it's sort of a difficult language to program in, and it's also a difficult language to specify because we've got lots of duplication. So we're going to add some syntactic sugar. And to add a syntactic sugar, what we're going to notice is a correspondence between the compile time terms and the runtime terms. So for example, we've got variables at compile time, and the ASTs are runtime variables, same for lambdas, and same for application. So instead of having all of this duplication, we're just going to introduce some shorthand, and that shorthand is going to let us convert between the two sort of coupled forms. And that shorthand is a quotation, which is the double angle brackets, and a splice, which is the dollar. And what quotation means is it says interpret the expression as an AST, and what the splice means is don't interpret this expression as an AST. And importantly, we start by interpreting things in AST mode because we model compile time metaprogramming, and this lets us write normal programs without any metaprogramming. So this was the example that we had earlier. We can write it in the code splice form, and what we say is that the code splice form means the AST form. Formally, we define an elaboration from the code splice form into the AST form, and I'm going to show you what that elaboration is now by walking you through the elaboration of this particular code splice program. So we're going to start off with a top-level splice. That's a splice not surrounded by any quotes, and the reason why we have that is because, once again, we start in AST mode. And starting in AST mode is sort of equivalent to having these ghost brackets around everything. So we start by converting things to AST. The splice tells us to stop, which means we interpret the application as just a regular application rather than the AST of an application. Then we convert the function. We see the quotation, so we need to convert the plus into the AST of a plus, and then convert the left and right-hand sides. When we convert the left-hand side, we see the splice that tells us don't convert the x. This just gets converted to the AST of a 0, and this gets converted to the AST of the 1. And then we get our original program back. So this completes the model. We had compile time evaluation and runtime evaluation, but we have an initial step, which is elaboration from a code splice language to a language with ASTs. And we're going to give these languages names, so I don't have to keep referring to it as a code splice language. We're going to call it lambda code and lambda AST. We're going to say that lambda code has expressions and lambda AST has terms. I think in the paper we've got lambda code op and lambda AST op because by this point I've introduced effects, but that's just something to keep in mind. So that's our initial model of metaprogramming, but I didn't say that MacroCamel was about metaprogramming. I said MacroCamel was about typed metaprogramming, so we need to add types. Let's start by adding types to lambda code. And in lambda code, what's interesting is that we've got compile time types and runtime types. For example, we can have naturals at compile time, and we can have naturals at runtime, and the two shouldn't be able to interact. You can't add a compile time natural to a runtime natural, for example. So to distinguish between the two, we're going to add these things called level annotations, -1 for compile time and 0 for runtime, and that just makes sure that we keep them separate. Similarly, we enforce a separation between compile time functions and runtime functions, but this is a very complete separation, and in order to do metaprogramming, the stuff at compile time needs to somehow manipulate the stuff at runtime, the ASTs of the stuff at runtime. So in order to do that, we expose an image of the runtime types in compile time, and to do that, we have a compile time type constructor, the code type constructor. So for example, we can convert runtime functions into the compile time code of runtime functions. And what quotation and splice do at this level is that they simply convert between the sibling coupled forms. So that's the type system for lambda code. We also add a type system for lambda AST. It's a lot simpler. We just add an AST type constructor for the AST forms. We had an elaboration from lambda code into lambda AST terms. We are going to do a similar elaboration for types. Remember that lambda AST is designed to be run at compile time, which means that compile time, naturals just become regular naturals, compile time, functions become regular functions, and runtime naturals and the code of runtime naturals become the ASTs of naturals. So now we've got our languages and we've got our type system. We can ask, what's the type preservation theorem? And the type preservation theorem has the same shape it always does, which is that well-typed terms don't get stuck. And importantly, they don't get stuck at any point in the process: elaboration, compile time evaluation, or runtime evaluation. So how do we prove this? Well, first of all, can we prove this? And second, if so, what can we rely on? Well, first of all, we have that well-typed terms don't get stuck at elaboration. So well-typed lambda code expressions elaborate into well-typed lambda AST terms. This is something that we prove in the paper. We have that well-typed lambda AST terms don't get stuck. This is kind of easy to prove. And we have that our runtime language, which is just a lambda calculus with arithmetic, doesn't get stuck, which is fine. But that's all we need. We need an additional lemma, and that lemma is that the lambda AST normal forms are ASTs of well-typed runtime terms, because we need to know that we've got a well-typed runtime term. And that's not what I said earlier. I said that lambda AST forms are ASTs of runtime terms. And there's a reason why I said that, and the reason is effects. And rather than giving you our formal account of effects straight away, I'm just going to add exceptions, and we're going to see how even exceptions cause a problem. So once again, we start, so this is a program that causes an error. We start once again with a top-level splice that just tells us to interpret it as a regular program. We install an exception handler, and we try and construct the AST of a lambda. That is the AST of the lambda. We're going to try and construct the body now. I'm going to skip a few steps, but basically how we're going to try and construct the body is we're going to first raise an exception and then return the variable. So that's how the elaboration works. Now we can try and run this lambda AST program. When we try and run it, we're going to raise the exception. The payload, var x, is going to get bound to z, which we're then simply going to return, and the entire program is going to step to the AST of x, which is, of course, not well-typed because x is free. So well-typed programs do get stuck, and this is scope extrusion. Right? This is the interaction of metaprogramming with effects. It's actually a very specific type of scope extrusion, which we call lazy scope extrusion, but I'll get into that distinction later. Although this example is caused by exceptions, scope extrusion can be caused by a whole host of effects. So that's scope extrusion. How do we solve scope extrusion? And one potential approach is to change the type system for lambda quote and lambda AST, so that scope extrusion programs do get stuck. Aren't ill-typed. We call this approach static prevention, and it's well studied in theory, which is great, but it tends to limit how effects can be used. And as I've said earlier, it requires wrangling with the OCaml type checker, which I really didn't want to do. So that's not what we're going to do. Instead, we're going to ask, can we check for scope extrusion and raise compile time errors when we run the lambda AST program? And this approach, which we call dynamic checking, isn't that well studied in theory, but empirically it tends to allow more flexible use of effects, and it didn't require me to modify the type checker. So that's what we're going to do. If you're curious, there are approaches that modify the type checker. I think contextual squid's a good example of that. So now we're going to study dynamic scope extrusion checks in theory, and we're going to start by asking the question, what is a dynamic scope extrusion check? And the key insight is that here we're using an elaboration to give a meaning to quotation and splice. And currently, the lambda quote program means something that runs to something that when it terminates returns a free variable, or the AST of a free variable. But that's not actually what we want it to mean. What we want it to mean is something that raises an exception at runtime, at compile time. So we need to change the meaning of the quotation and splicing, which means we need to change the elaboration, and we need to change the elaboration in such a way that it inserts checks, and these checks can raise exceptions. So that's what a dynamic scope extrusion is in our model. It's just an elaboration that inserts checks. So a very natural question to ask is, how should we insert checks? And different answers lead to different types of dynamic scope extrusion checks. The first option is to evaluate all the way until the end and then perform checking. We call this the lazy check. So let's see how it works. We start off with a lambda code expression that we elaborate into a lambda AST term, which we can then run until completion. At the very end, we check the normal form that we get to make sure that it doesn't have free variables. This is a really simple approach, and it's really good in some ways. We say it's correct and it's maximally expressive. These are technical terms that, if you're familiar with static analysis, correspond to soundness and completeness. But there is one problem with the lazy check, and that is it's horrible to use in practice. And the reason why it's horrible to use in practice is because you have to wait until the very end. And because you wait until the very end, you lose a lot of information. There are no stack traces. You have to wait for the entire program to compile before an error is reported, and I guess that's fine if you want to go drink a coffee rather than do work. And also variables can be bound in really nasty ways. And I don't go into this in the presentation or in the paper, but we do point to research that talks about this. And you don't have to take it from us. This is what Offenbach and all say when they use the lazy check to build the RAND-IR system. They say that errors are reported in very obfuscated ways, precisely because you're waiting until the very end. So the lazy check isn't great. Another option, therefore, is to check whenever an AST is built. And this is the check. We call this the eager check, and it's what's used in Meta OCaml. So let's be a little bit precise about what it means to build an AST. Here's a program where we build the AST of 2, bind it to X, and then return X. When we return X, that's not building another AST, that's simply returning a pre-built AST. I hope that gives you a sense of what it means to build an AST. We can look at the trace under the eager check, and importantly, we're not just going to check at the very end, but we're going to check at various points along the way whenever an AST is built. I think it's important to take a step back here and realize that the eager check uses a different definition of scope exclusion than the lazy check. So for the eager check, a free variable in T2 is bad and will cause scope exclusion that will be reported. But it might not cause scope exclusion under the lazy check because the lazy check is a free variable at the very end. And maybe that free variable won't appear. So lazy scope exclusion checks for free variables after code generation, after the entire process, right? Once you have your normal form. Whereas eager check checks along the way. So obviously these are different definitions, but we can ask, do they coincide? Do they happen to be the same? And returning to our example, we can ask, must the free variable in this case, T2, show up free in the normal form? And here I'm assuming that compile time generation terminates. Well, no. First of all, that free variable could be thrown away. But second, perhaps it could appear, but appears bound somehow. That first problem isn't really a problem, because if you throw it away, well, I don't really mind reporting an error there. But that second problem, let's investigate whether or not free variables can appear bound in the end result of program generation. And in order to ask that question, we need to ask a different question, which is, can we capture a continuation containing a binder and reinstate it? Because if you can, then we can take free variables and make them bound again. And the answer to this is slightly complex. Not technically complex, but historically complex. The answer is that it wasn't common when the eager check was introduced in 2014. And in fact, this is what Oleg says. The ability to re-enter scope, dynamic scope was uncommon at the time. If you can, well, it results in false alarm. That was in 2014. In 2022, effect handlers were added to OCaml. And effect handlers give us precisely the ability to restore safety once we enter scope exclusion. So, brief tour of effect handlers. Here's a program that raises an exception R with a payload 0 and then returns 0. We're going to ask, can we handle the exception R by going back to the point where it was raised and replaying it with a value of our choice? This is an operational account of effect handlers, and that's really the only account that we need. So we need a definition of what that point is, the point where the exception was raised. And we define that point as a continuation. That's the stuff that would have been done at that point if the exception had not been raised. In this case, we're just adding 1 to the result. And we're going to bind it to K, the continuation. We're going to introduce a new keyword, continue, that lets us go back into the hole and plug it with the value of our choosing. That lets us go back to the point the exception was raised and resume. And here I'm choosing to resume with 0, but I could have chosen to resume with another number like 3. Some syntactic differences between effects and exceptions. We use handle instead of try and perform instead of raise. That's what effect handlers are, and what they do in our case is that they give us the power to recover from scope exclusion. Here's an example of a Lambda AST program where we perform an effect. When we perform an effect, we take the payload var x and we bind it to z, which we then substitute into the plus z0 expression. So we get the AST plus var x 0. And this, note, var x is not bound in the AST in this case, so this is eager scope exclusion. But we also generated a continuation, and that continuation has a binder for x. And in fact, we use the continue keyword to plug that malformed AST back into a scope in which it's saved. And so the free variable that would have caused eager scope exclusion appears bound in the final term and does not cause lazy scope exclusion. So resuming continuations can restore safety after eager scope exclusion has occurred, causing exactly the false positives that Oleg talked about. That's a problem, but in our opinion, that's not the biggest problem. To see the biggest problem, we're going to translate this Lambda AST program into its Lambda code equivalent, and we're going to call it B. And here I'm going to act like an optometrist, because I'm going to ask you, do you think there's a difference between B or A, or do they look the same? And the important difference to note is that B has that plus 0 and A doesn't. And the question that we're going to ask is, so we know that B fails the eager check and is a false positive. Is A also a false positive? And the answer, somewhat unintuitively, is no, it's not. And the reason why is because that plus 0 builds an AST, and that doesn't. That returns a pre-built AST, which is really unintuitive until you expand it out. So we didn't like that, and we wanted to design a check that lets B pass as well as A. So neither B or A would be false positives. And that's our novel check. And what we do is we check at different points. What we do is we wait until all continuations are gone, and then we check eagerly. And we call this the cause for concern check. So we can look at how it looks like operationally. What we do is we change each check into something called a check M. A check M is like a smart check. It's aware of continuations that are still on the stack, and if it sees any, it erases itself. And so consequently, in the earlier example, we can not report an error in B, so it doesn't become a false positive, because we see K, and we know that it's still around, and we know you could use it to resource safety. So the C4C check uses its own definition of scope exclusion. Like the eager scope exclusion is defined in terms of intermediate states, because we want to report scope exclusion early. But unlike eager scope exclusion, it's not just a free variable in an intermediate state, but it's a free variable that must be free at the end result of evaluation. So that simulates the lazy check, or that has the same idea as the lazy check. And so that characterizes our goal. We want to catch lazy scope exclusion, not eager scope exclusion, but we just want to do it earlier. So our C4C check is correct, but it's not, unfortunately, maximally expressive. And this is a program that causes it to not be maximally expressive. This is a false positive. I don't really need you to know what it does, but after elaboration and evaluation, we get this. And what's important to note is that we build an AST with a free variable, y, and at that point, there are no continuations left on the stack, so the C4C check will fail here. And this shouldn't be surprising, because earlier I said that there were two ways, and if we had continued, the malformed AST would have been thrown away, and we would have returned the well-formed AST of 0. And this shouldn't be surprising, because earlier I said that there were two ways in which scope exclusion at intermediate points might not show up at the end result. First of all, you can rebind continuations. You can use continuations to rebind free variables. And second, you can throw unbound variables away. And I only solved the first one. Here, we're still throwing unbound variables away. But all false positives look like this. And we formalize this in a cause for concern property that states that if our cause for concern check reports an error, the only thing you can do with that AST, the only valid thing you can do with that AST to resource safety is to throw it away. So I don't mind reporting a false positive in that case. That's basically it for the presentation. There's a lot more in the paper that I didn't have time to talk about today. There's also an artifact and an implementation of the C4C check in MagoCamel, where we empirically validate the claims of this presentation and the paper. But in this presentation, I've introduced a theoretical framework for studying dynamic scope exclusion checks. I've used it to encode, compare, and evaluate existing dynamic checks. And I've introduced our novel C4C check that is designed with effect handlers in mind. Thanks very much.
Any questions for Michael?
Thank you for a great talk. Yeah. So my question is very simple. Well, you stick to compile time metaprogramming, well, but many ideas came from MetaOCaml or Orexero. Does your result hold for also for runtime metaprogramming?
Yes, so that's a great question. I believe it does. Compile time metaprogramming and runtime metaprogramming look very similar at first, but they're actually quite different. However, I think in our calculus happens to operate in the exact subset in which they coincide. So I think our approach extends to runtime metaprogramming. There are practical trade-offs. For example, although ours is a dynamic check, our errors are still reported at compile time because of compile time metaprogramming. But in terms of, I think the properties that we have, it should extend that quite naturally.
We've got time. Question in the middle. If someone can get a microphone now.
Thanks for the talk. I also have quite a simple question. Here, scope exclusions, so you need to check for them because you have effects kind of in the object language. But if you only have effects in the meta language and not in the object language, you don't need scope exclusion checks. Am I right?
Right. So so scope exclusion occurs if you have effects in the meta language. That's the compile time language, the language that performs the code generation. So if you only have effects in the runtime language, so if you only have effects in the, like if you only have the ASTs of effects and not effects themselves, then you're fine. That's correct. So if your compile time language is pure, and that's a completely valid approach. So you prevent scope exclusion by saying everything you can do at compile time is pure. But we wanted effects at compile time because when you have effects in your meta language, in the language that does code generation, you tend to be able, it's a lot easier to implement certain optimizations like loop invariant code motion because you can lift things outside particular scopes, right? If you lift them too far, then it becomes scope exclusion, but you can lift them just a little bit, and then you get things like loop invariant code motion.
Thanks.
I think we'll move on to the next talk now, so could we thank the speaker? So next up, we'll have Donica talking to us about hyperfunctions.
Hiya. Thanks very much. So this is joint work between myself and Nick Wu. I realized on the way over here today that I'd accidentally dressed like Steve Jobs, but fortunately I'm not going to be introducing the iPhone or something. It's just going to be hyperfunctions. So what is a hyperfunction? Subject of this paper, it is a type, this one here. So it's a recursive type. A hyperfunction, I denote it with this kind of weird-looking arrow here. From A to B is a function that returns a B and takes a hyperfunction from B to A. Okay? This gets a little bit clearer if we expand out the definition one level here. So notice that the order of arguments to the hyperfunction flips on the recursive call. And if we go even one layer more, so notice that all of the B's here, so it's going to be an infinitely left-nested thing, and all of the B's are going to be in positive positions, so it's either going to be returned or to the left of an even number of function arrows, and all of the A's are in negative positions. So in some sense, a hyperfunction takes in a bunch of A's and produces a bunch of B's, kind of, right? There are a lot of different ways that you can kind of develop an intuition for hyperfunctions. We're going to go through a couple of them, but noticing the polarity of the A's and B's is handy. Right. So, first of all, just in terms of the definition itself, it's an infinitely left-nested function. It's also really related to continuations. In particular, we can notice that the standard Haskell definition of the continuation monad, when the two arguments of a hyperfunction coincide, it's the same as the fixed point of that continuation monad. So cont there is just Haskell's cont monad. The other interesting thing about it is it shows up all over the functional programming literature. So all of these papers have types in them that end up being equivalent to the hyperfunction. And they all actually do similar jobs. So they all seem to show up whenever continuations and concurrency get combined. Okay, so what I want to do first is just go through a few of those examples of where hyperfunctions have shown up in the literature. And then so we can develop an intuition for the patterns that give us hyperfunctions. So the first place is in trying to fuse zip. So Haskell performs list fusion as an important optimization, or GHC Haskell does. And this is an optimization that applies to list functions like map, filter, and concatenation. And the basic idea of it is to remove unnecessary passes over lists. So this is a kind of a classic example of one of the optimizations it performs. Those two expressions are equivalent. List fusion will rewrite the left-hand side expression to the right-hand side one, right? So map F after map G is the same as one map where you use the F after G. The way it works is we rewrite all list consumers to a common form that uses this fold_r function. And then we have some rewrite rules that apply to fold_r. And good producers is the other side of the thing. So if you rewrite it to fold_r, it's a good consumer, and then that can interact with good producers in a way that eliminates the intermediate passes. So zip initially was thought to be the exception to this rule, right? Like we can apply map, filter, and concatenation, we can fuse them away. Zip seems a little bit more difficult to do. So this is just this definition of the zip function. Maybe it's a little bit more helpful to see an example there. So it just takes two lists and it combines the elements pairwise, right? Yeah, so while it is possible to fuse one of the two arguments to zip, and while it's possible for zip to produce lists in a well-behaved way, it's very tricky to see how can we make this fuse on both input arguments. So the solution to this problem was presented by Lansbury et al. In the paper that also coined the term hyperfunctions, right? I'm not going to show you their full solution here, but I'm going to show you just one of the kind of the steps that you can do if you try and get to their solution yourself. So what we can try to do is fuse zip ourselves just by kind of like blindly applying whenever we see a pattern match on cons and whenever we see a pattern match on nil, we're just going to replace that with fold_r, right? So we'll grab the zip xcons x's clause and we'll try and put all of that into the 3 dots for fold_r there. There's a little bit of ingenuity that you need to apply here, but if you keep going with this, you will eventually hit an interesting type error. Unfortunately, you don't get this exact same type error in modern GHC. It gives you something a little bit more probably practically useful, but for our purposes, this is quite cool because this type error that we're presented with here when we try and fuse away zip is GHC telling us that it can't unify the types T0 and then this thing on the right-hand side, T0 to whatever, to whatever, to whatever, right? But even though GHC can't unify the types, we can. We can just go to that place where it has that pesky not equals and stick an equals in instead and put a new type on the left, and then we have a type that satisfies the inequality. So this new type zip, if you see the definition of it, it's the same as the right-hand side of the type error above. And this zip type is a hyperfunction. So this type is an instance of the pattern that we saw on the first slide. So this is our first example of a hyperfunction. So another one came in an email to the types mailing list containing an algorithm for breadth-first traversal that included this type on the top right there. This is from Martin Hoffman. And the interesting part about this kind of algorithm was the fact that this type is not strictly positive, and there's some interesting implications to the, on the theory side for that. But for me, what was interesting is that this is another hyperfunction. So this type doesn't match precisely because roux contains an extra constructor, but the structural similarities are completely there. The difference is really superficial. So this is another example of a hyperfunction being used to do something quite different from what we saw earlier. And this is actually the first hyperfunction that I was able to find anyone using. So the other example that I have is in optimizations of coroutines libraries. So coroutines libraries like pipes in Haskell let you write kinds of programs where yield 1, yield 2, yield 3, and that gets converted to a program that iterates through 1, 2, and 3 and returns those. And then you have another coroutine which awaits them, and you can join them up and so on. If you read these things in the direct style, they can be quite slow. It's very easy to accidentally write quadratic code in your implementation of coroutines. And so Michael Spivey wrote a paper on how to optimize, in particular, the API provided by the pipes library. The thing is, the normal optimization that you would want to apply here is you would want to CPS encode it. You would want to write the whole thing using continuations. Except it's really difficult to write merge in this case. And in fact, if you do it initially, it seems impossible. It seems like you're not going to zip two coroutines together. Yeah, the problem is merging two coroutines in parallel. A core component of Spivey's solution involved these two types, incont and outcont there. And would you be surprised to see that those are actually hyperfunctions yet again? So there's another example of hyperfunctions in the literature, and we have a few more here. So this is a paper on transducers, where hyperfunctions were used in the underlying representation, or to be specific, the underlying representation contained types that were equivalent to hyperfunctions. This paper implemented algebraic handlers for the pipes library, and in it, these two types were used, which are again instances of hyperfunctions. In fact, these are equivalent to the incont and the outcont that we saw in Spivey's example. So why do we care? What's the point of noticing all of these different things in the literature? So it seems like there's a common pattern here that whenever we try and CPS encode an algorithm that performs parallel merging, we have to come up with this hyperfunction structure. And secondly, it is a real headache to figure out how it works. It's a weird looking type. Programming with it is very difficult. Very often when I would come across an example of a hyperfunction in the literature, the authors would remark, by the way, this was horrible to work with. This was really difficult to figure out. Also, the examples I gave, I think that to the best of our knowledge, we are the first people to notice that they actually use the same underlying pattern. Okay? So there's this pattern out there in the functional programming world that is very, very tricky, very difficult to understand, and people don't recognize that they are struggling with something that has already been worked on in other places. So my goal with this paper is to try and raise the profile of hyperfunctions a little bit so that people can recognize when they might be applicable to their problem, when they might be usable in their use case, and also maybe give a little bit of a framework for and a toolbox for working with hyperfunctions. So let's do that now. So a lot of the work on building an interface to hyperfunctions has been done already. So hyperfunctions themselves form a category, and there are a bunch of other handy combinators you can use to work with hyperfunctions. So we have the interface up there on the top right. So you can compose hyperfunctions. There is an identity hyperfunction. That triangle thing. You can treat hyperfunctions like a stream, where you can push functions onto the top of the stream. And on top of that, Ed Komet's hyperfunctions library is fantastic and has a huge amount of really, really useful combinators for working with them. Our paper contains a bunch of worked examples on using hyperfunctions to implement functions. things like comparison or subtraction on church-encoded natural numbers, the zip example, I think another example as well, so that should also be helpful. Yeah, so I want to emphasize the cases where I think that hyperfunctions will come in useful to programmers. So when you're programming, you encounter a problem, when should you be thinking about maybe hyperfunctions are the thing that I need to employ? So we've seen that they're useful at the intersection of continuations and concurrency. Broadly, if you have some kind of program or some structure that you're working with that is encoded as continuations, and you want to communicate between two processes in that thing, or transfer control between them, then hyperfunctions might be what you need to employ. Very narrowly speaking, if you have two continuations encoding and you need to interleave them, it's pretty likely that hyperfunctions will be useful in that case. The examples that we've seen so far are that somebody tries to encode a structure using continuation passing style for performance reasons, and one of the functions in the structure needs to be done in lockstep, and then they discover, oh, this is really difficult to do, and that's where the hyperfunction comes in handy. Great. So now I want to talk a little bit about the theory of the type itself. So the first thing is hyperfunction as a type is quite weird. It contains recursion to the left of the function arrow. It's also non-regular, so the type parameters flip on every recursive call. So for the first of those reasons, it's not admissible in set theory. The cardinality of this type is all over the place. You don't yet get to use the traditional tools you might want to for talking about the theory or the foundations of this type. Especially annoying for me, it's not admissible in AGDA. So because this type is not strictly positive, and in some cases not positive at all, we can't just drop it into AGDA and prove all of the things that we'd like to prove about it. You have to go quite a bit out of your way to make sure that you are dotting your I's and crossing your T's. You have to really check that, this paper presents a handful of techniques of embedding Martin Hoffman's root type that also apply to the hyperfunction type. The second interesting thing about hyperfunctions, I've mentioned that they seem to capture something about the essence of concurrency and continuations. A significant part of the paper is trying to make that notion concrete. And we do so by showing that hyperfunctions can form a fully abstract model of the calculus of communicating systems. So hyperfunctions are at least as powerful as the model of concurrency that's captured by that. This is a calculus that supports non-determinism, parallel merging, and communication. It's a basic standard calculus for these kinds of things. And interestingly, our model is similar to other message passing uses of hyperfunctions in that so the communicator is our model on the bottom right there. The structure of that hyperfunction bears a strong resemblance to the structure of the hyperfunction that we used when encoding zip or when encoding any of the other message passing instances, right? So it actually uses the same principles, the same tricks, and the same kind of structure. On top of that, our implementation is pretty short. You can see it on the right there. I don't expect anyone to understand that, but just note that it's quite compact. It's not a tortured implementation of CCS. It seems to be quite naturally embeddable into it, and as a result, I think it's strong evidence that hyperfunctions do capture something about the essence of continuations and concurrency. Great. So now I want to talk a little bit about some new uses of hyperfunctions. So these are examples, longer worked examples that we have in the paper on how hyperfunctions can let you do some slightly more powerful things. So first is concurrency monad. So there's this classic functional Perl on a poor man's concurrency monad that embeds a concurrent language into Haskell using monads. It's a standard language that has fork, and it's a monad transformer, so you can lift effects from some other monad, and then you get to evaluate them in a concurrent way using some standard concurrency primitives. What's interesting about this paper is if you, the scheduling algorithm in the paper actually performs a kind of a breadth-first traversal over the AST of the concurrent language itself. So what we can do is we can recall Hoffman's algorithm for breadth-first traversal that uses hyperfunctions, and we can try and apply the same thing here. So we can re-implement the scheduling algorithm from the concurrency monad paper using hyperfunctions. And then actually we can go a step further than that and cut out the middleman entirely and build the whole language in this paper out of hyperfunctions entirely. So the language itself is given as that conc type on the top right there. It's the continuation monad wrapped around a hyperfunction. This is a monad transformer in M, so that atom function will lift an effect from M into the conc thing. The main operation that you get in this language is fork, so you can fork a conc computation and let it run, and then of course run at the end, so you can run the thing using all of your desired scheduling back into the underlying monad. Cool. The other example we have is our own encoding of coroutines. So this takes a lot of inspiration from Shivers and Bytes continuation-based transducers. In particular, one of their encodings towards the end of the paper is based on these two types up here. So a channel and then this switch function, which lets you send a message to a coroutine and receive a response. And if you look at that channel type and you look at the recursion pattern that it uses, it should remind you quite a bit of the hyperfunction type that we've been using so far. And indeed, that channel type is pretty integral to our encoding. The benefit that we get from our encoding is that we get this send function. So often in continuation-based encodings of coroutine libraries, you can merge two coroutines, and then all of the yields from one coroutine will get lined up with the awaits in the other coroutine, which is great, but it's quite difficult to implement a function like this, send, where from outside of the coroutine, you actually send a value to the coroutine, and then you want to get back its response and the rest of the coroutine. This is difficult to encode kind of for the same reason that it's difficult to write uncons on a church-encoded list or tail on a church-encoded list. Yeah, you kind of have to turn the continuations inside out. It's very tricky, but hyperfunctions let us do it. And yeah, that's all I have. So thanks very much.
I think we maybe have time for a couple of questions.
Thanks for an interesting talk. So yeah, one of the examples was from my paper on handlers in action, the pipes we implemented there. So it was, the implementation we did with deep handlers of pipes was very convoluted, and I can see the connection to hyperfunctions. But if one switches to a different notion of handlers, shallow handlers, or better, some kind of multi-handlers, as in Frank, then the definition of pipes is really straightforward. What's going on there?
I'm not, so a similar thing like that happens actually with fusion. So you can also do stream fusion instead of the fold-R-based fusion. And the stream fusion doesn't run into any of the difficulties with zip. All of that stuff kind of falls away. But it seems like the two things are dual of each other. with relation to hyperfunctions. So what I would expect is that the hyperfunction encoding, it's very difficult to encode the zip-like things or or the coroutine handlers, but it probably has advantages in other respects, if that makes sense. So the hyperfunction lets you fuse away inductive things, and it's very difficult to do on merging, but I think that in the case of folds, for instance, it lets you keep up your fold fusion machinery elsewhere. So I wonder, is there a similar trade-off, basically?
Thanks.
Any other super quick question? Okay, I actually had one super quick question myself. So you had the library in the, you showed some like library functions in the middle, and you showed you could run a hyperfunction from A to A.
Yes.
Is there a more general way to run hyperfunctions that are not from the same type to the same type? Do you?
Yeah. So.
Sorry, sort of right in the middle.
No, there's no problem. So you get this run type on the top right. So the other main way that you would eliminate out of a hyperfunction is a hyperfunction from A to B. You apply that to a hyperfunction from B to A, and you get a B out. So that would be the most general way of exactly. Yeah. Okay.
Let's thank the speaker again and move on to the final talk of the session. Okay, so we'll end with Rodrigo telling us about linearity in a lazy setting. Thank you.
Right, hello everyone. I'm Rodrigo. Me and Bernardo Zanin, who's there, wrote lazy linearity for a core functional language, and here we are. So linear types, you've all seen them before. Here are two very quick examples. We have a bad function, highlighted in red. Say a linear function, its main property is that it consumes its argument exactly once. So on the left, we have a bad linear function that takes a pointer and must use it exactly once to produce an IO action. This example, it takes the pointer and then frees it twice. So this function is rejected. It's definitely not linear because pointer is being used twice at runtime. On the other hand, we have OK, which is also a linear function from pointer to IO unit. It takes the pointer, frees it once. It's all fine, so this function is accepted, and it is in fact linear. So right off the bat, I want to get a question and maybe a show of hands for this function, and the question is this function linear? And this is an interesting function which is linear from pointer to IO unit. It takes a pointer, it let binds baz to free pointer, then it does some condition. In the true case, it'll return baz, which is the let bound value, and in the other case, it will just free the pointer. So perhaps we can have a show of hands for whether this function is linear. Do you think that it is linear? Is pointer being used exactly once, is the question. Right. So perhaps not many people are convinced, and I want to answer with, it depends on the evaluation strategy. So if the function is being evaluated strictly, then baz is evaluated right away. We evaluate free pointer right away, bind the result to baz, and then in the event where we have, where we get into the else case, we'll be freeing the pointer again. And in that case, it just surely isn't linear because at runtime, pointer is being used twice. But if this program is being evaluated non-strictly, say with lazy evaluation, we will just bind baz to a thunk, which would free pointer if it is evaluated. But if it's not evaluated, then all is fine. So in the true branch, we would return baz, therefore evaluate free pointer, we'd free the pointer once. In the else case, we just free the pointer. Baz is unused, and therefore we never compute free pointer twice. We have just, at runtime, used pointer linearly. The problem is that there's no type system that can see this. Right, so as far as we know, all type systems will just reject this program. And that's because traditionally, linearity is just too syntactic or too strict. And so the lazy semantics of linearity, which appear with lazy evaluation, are just rejected. a key observation is that syntactic linearity is not necessarily the same as semantic linearity, at least under a non-strict language. So you could say, fine, we just type linearity strictly, why do we care? Okay, so of course we want to be able to be flexible, we want to accept more programs. Linearity is already somewhat burdensome to work with, and if we could just accept more programs as linear, that'd make our lives easier. But there's also a very real-world problem in which this, a real-world project, which is GHC, the Glasgow Haskell compiler, in which this problem occurs. So, as you know, we have linear types in Haskell for a while now, and linear Haskell is desugared into this core intermediate language. And core is both lazy and linear, which is, not all languages are both lazy and linear, but core is. And core is optimized over and over again, and this changes the structure of the program a lot. Of course, core is typed, and that serves us very well because we can use the type checker as a source of sanity checking for the intermediate language and the optimizations that GEC does. If it type checks still after, it's probably fine. But linearity is just currently ignored altogether in core because we'll see. It's because of this problem that because laziness and linearity are currently just not understood by type systems statically. And of course, if we don't have linearity in core, then we also can't use it for optimizations. That's something that'd be cool to do. So it's just, this advantage is not to be able to type programs like this one. So linearity is just dropped. As soon as we get to core, we just ignore it completely because optimizations destroy the syntactic linearity very easily. We have an example here where we do inline, we inline let y equals 3x in y. So y is in line, and then we have let y equals 3x in 3x. And this is already problematic. Maybe we drop the binder afterwards, but we type check all intermediate results in the program. And this one is already rejected before we even have the chance to drop the binder. Because y, again, is not used and core is lazy. In our paper, we have this type system which does accept the lazy semantics of linearity statically. We've got a soundness proof over this instrumented big step semantics that tracks resource usage at runtime. So the soundness proof over our type system also guarantees that a well-typed program will consume at runtime resources linearly. And we also prototyped it as a GHC plugin, which we introduced into the core pipeline of GHC to try and type check every intermediate program, and we had very good results. But on this talk, I want to focus on the core ideas for typing linearity in the lazy setting statically. So first of all, lets, and lets are the simplest to handle. We have the same program that we saw before in the introduction, and note resources in the lets are only consumed if the binder is evaluated. So let's try and type this. The key idea is, okay, let binding doesn't consume resources, so we're just not going to consume resources in the typing derivation. Instead, we'll annotate the let variables with the resources that were used in its body. So y here, we have let y equals free pointer. So y is annotated with pointer because that's the resource that we have. So I'm just going to type this example. We have two contexts, the unrestricted context to the left side of the semicolon, and we have the linear context. So variables in the linear context must be used exactly once, and the others can be used as many times as you want. And then we want to type the full let. So we use pointer to type the binder, and okay, that type checks. And now we do not remove pointer. So in traditional linear type systems, you'd have to split pointer either to the binding or to the body of the let. In this case, we just have it in both places. But we also introduce y annotated with the pointer resource, and then when we use y, it'll consume pointer indirectly. So this is how linearity is in a traditional linear type system. We have two contexts. Well, we have one linear context split into two to type the let. We use the first part of the context to type the first expression, and we use the second part of the context plus the variable that was bound to type the second expression. So you see, delta 1 went to one side, delta 2 went to the other side. They never are reused. And now compare this against the typing rule for let in our system. We have the same context splitting. We use it to type the expression which is let bound, and then to type E2, we still have both parts of the context. We don't consume delta 1 at all while typing the let binder. And now we introduce y unrestrictedly. And it's important that y is unrestricted because we may want to drop it. We could just use x directly, and we could just use delta 1 directly, and so y can just be dropped. But if it is used, then it'll consume the linear resource. That's what it looks like in the variables rule. So this is for traditional linear variables. We also have this rule. So if you want to type an x, and you have an x in the linear context, you just use it. Now, if you have an annotated variable, you want to type y, and y is annotated with delta 1, then the linear context must be exactly delta 1. That's that there. Right, so lets are easy because they don't do any evaluation, only at its use sites. Cases, on the other hand, drive evaluation, therefore that makes them slightly more, well, considerably more subtle. So I want to go through a couple of examples. We have pattern matching on a tuple, which is already evaluated. This is just x, y. We match on A and B, and then we do something with both A and B. This is already accepted in linear Haskell. This is accepted traditionally. But now here's something else which is kind of similar, but is already rejected by traditional type systems. We match on x and y, we bind A and B, and then we do something with x and y and ignore A and B. Well, this is fine because x is just y, sorry, A is just x and B is just y. They're the same program. This is highlighted in yellow because our type system accepts it. Now here are totally not fine programs. We evaluate, we scrutinize free x, and scrutinizing an expression forces its evaluation to weak head normal form. So we scrutinize free x, that'll surely do something to x. And now we try to use x again, that's not fine. Here's the second example in which we use x somehow, and then we match on v and ignore v. That's also not fine, because use could be identity, and if use is identity, now we're just ignoring x in the continuation of the let. So this is also not fine. We must make sure to consume the matches if we have a non-weak head normal form expression there. Case expressions drive evaluation, consuming parts of resources. So the idea for typing lets, one of the main ones, is that we have to have two different rules based on whether the scrutiny of the expression is or not in weak head normal form. And this is a static property as well. So in this case, this is the same example. X and Y is in weak head normal form, so we type it differently to this expression which is not in weak head normal form. Again, these programs may seem stupid. No one would want to write them, but the compiler will just produce tons of them, and we must be able to type them. Right, so for weak head normal form cases, it's easier because we know that the weak head normal form will match one of the patterns. So here x and y will match linearly to both A and B. So we will just do the same thing as a let because the bound variable in the pattern is not going to be evaluated. So we just have A is the same as using x and B is the same as using y. And so then when you use x, y, that's fine because A and B were introduced in the context similarly to the let. So yeah, we have x and y, x and y types the scrutiny, and then we still have x and y, and we now have A and B which have these aliases, this list of resources. And now you could either use A or B or x or y. Well, you have to use both x and y or A and B or A and y or x and b, so you can do this kind of combination, and it'll all be accepted. So we're just trying to delay as much as possible, consuming the resources. Now for not weak head normal form case expressions, the resource is just going to be used, really used, so we have to do something about that. And the way that we do this is by introducing the variables which are used in the scrutiny as irrelevant in the continuation. So that looks something like this. We have x here, x is used to type the scrutiny, and now the continuation is typed with this irrelevant x that's annotated in brackets. So an irrelevant variable cannot be instantiated with a variable rule, so you just will never be able to use this irrelevant x directly at all. But if you have a variable which is annotated with an irrelevant x, then you can consume the irrelevant x through this variable. That looks something like this. Typing the continuation with an irrelevant variable. This one is rejected because we don't have x in scope. This thing is irrelevant, so you can't use it. Typing this is going to be a problem, because now you're ignoring the irrelevant X, which is consuming the rest of the resource, right? Here, you still have to make sure that V is consumed. And that's what this irrelevant X is doing. You have to use it because this is a linear variable. You just can't use it directly. So how do you use it? By using V. Right, in the paper, as I mentioned a few slides before, we have a soundness result over a linearity-aware semantics that guarantees us both soundness and that well-typed programs do consume linear resources exactly once. We also have a large set of optimizations that GHC does, and we prove that if the program before optimization was well-typed, then optimizing it results in a well-typed program as well. So that basically ensures that our system is able to accept most of the transformations that GHC does, at least all the ones that we checked, and one more which is slightly more difficult to analyze, and that is in the paper. And we have also the GHC plugin, which had pretty good results. Right, linear core, which is the name of the system that we introduced, accepts more of the lazy semantics of linearity. Not all of them. There's some future work like multiplicity coercions, which go into where coercions and multiplicity mix. And it is suitable, this type system, for the lazy linear core language because of all the results about optimizations and the GHC plugin results. Of course, so I've been focusing a lot on linear Haskell and Haskell, but this should apply to other lazy linear languages. Not many of those exist, but it also applies or can be made to apply to strict language which have strict features, strict linear language with strict features. Yeah, right, that's what I have. Thank you.
And we have quite a bit of time for questions, so I'm going to have any to start us off. Yes.
Thank you for the talk. So I was curious about the small technical detail. So you showed this nice, compelling example for irrelevance, but it seems to me you could have solved the same problem by promoting the binder to be a linear variable itself. So is there a reason why you didn't do this? Is it just to have a unified treatment of binders?
If you promote the variable to be linear itself.
If we go back to the example.
Yeah, no, understood.
So V could be introduced as linear here.
Mm-hmm. V could be introduced as linear here. I want to say that I'm sure that I thought of that, and that's something that I don't recall exactly now why it's more complicated. Yeah, I would have to think more. At the moment, I don't recall. I would hope that that's not so simple. But I think there's something more complicated here, but I cannot think of it off the top of my head.
Okay, thank you.
At the beginning, you said that one of the things that you want from this is that for optimizations on core to take advantage of linearity. Do you have any examples of new optimizations that on core that can now take advantage of linearity?
Mm-hmm. Right, so there's a handful of references to this throughout the literature about optimizations, and it's often just a side comment which says, well, if we had linearity, then, for example, inlining, we didn't have to depend on heuristics. You could just use the linearity information directly. So that's one example, inlining. Yeah, that's the best example, I think. So inlining is heuristic, but if you have linearity, then you just know it's used exactly once. That's one example. But the other ones are future research. I think it'd be interesting to explore how linearity can be used for optimizations. It's currently not at all. You don't have linearity in core.
Thanks.
We've got a quick question from online, which is, did the GHC plugin find linearity bugs in GHC?
Come again, sorry?
Did the GHC plugin find linearity bugs in GHC?
Did the GHC plugin find linearity bugs in GHC? That's a very good question. Yes, so so the GHC plugin accepted the vast majority of programs that were produced by GHC, but not all. And the not all is the interesting part. Which programs are linear core is linear core rejecting? So some of them are technical details, like a rewrite rule, which is rewriting things which by ignoring linearity. So you take a linear function, and then some rewrite rule is just dropping the linearity information, and that is not allowed. It also saw how multiplicity coercions are necessary for some programs. And did it find any bug? I don't think so, but I didn't analyze all of the programs that failed because, yeah, it's a few dozen. And some of them could be real bugs. But very important to note, the GHC should not in any way, no optimization should ever be destroying linearity. It's very good that it doesn't. Because it'd be very weird if you wrote a source program which frees X once and then the GHC optimizer makes it so that it's freed twice. That's definitely not okay. Yeah, so as far as the plugin is concerned, I didn't find any specific bugs, but I found programs which were rejected by linear core, which hinted at real, what do you call it, limitations of, say, rewrite rules, for example, how they were defined. Yeah.
Question up there.
Hi, I had a question on the first example.
First of all,
the let y equals free x in if.
Mm-hmm.
So I can imagine like another way to write this program is, or like to compile this program or type check this program might be like let baz pointer prime equals free pointer prime, and then when I use baz, I sort of pass in my linear value baz pointer.
Yes. So today, if you wanted to make this program type check, you could make pointer an argument of Vaz. Is that what you're saying?
Yes.
Yes,
like
so that would be valid in linear Haskell today. Yeah, it'd be good if you can accept this directly, though.
Okay, thank you.
Thank you.
I had another question about this example. This might be a misunderstanding of my knowledge of Haskell, but could you use Baz twice here on one of the branches? To let things only get evaluated once if you use them twice?
That's a very good question. Right. So so what happens if you have a thunk which frees the pointer and returns unit? So the first time that the thunk is evaluated, it'll use and free the pointer and then bind unit. And then unit is fine. You could, in principle, just use the unit as many times as you'd like. And but what if the thunk is ID of x? And now forcing ID of x just returns x again. And then you don't really know. So here's one place where you have to be conservative. In principle, if it's lazy and not call by name, then at runtime there might be programs which you would reject, which would be fine because the thunk would be evaluated to something which had fully consumed the pointer. But you can't know statically if it is fully consumed. But that's a very good question. Thank you.
I have a question. So is there any program in your GHC plugin that is semantically correct with terms to linear types that you reject? So sort of, I guess, have you proven completeness?
Mm-hmm. So is there any program that appeared in GHC core in the plugin that my system rejected, but is still semantically linear? Yes. So, I keep thinking about this, but one of them was the rewrite rules. So you had some rewrite rule which made use of linear things in as far as the type of the function which got applied, it wouldn't be linear just because the function is unrestricted and is being applied to a linear value. But that would just be, at runtime it's fine, but at the type system it doesn't check. Again, the example with the thunks, like if you have a thunk which fully consumes a linear resource and returns some unrestricted thing, that unrestricted thing could in principle be used multiple times, but you can't check that statically.
Thank you.
Question at the back? No. Okay. Okay, I think we'll leave it there. So I think the next thing is lunch. So let's thank our speaker one last time. And thank you to everyone who presented this session.
Okay, do you want to check? Oh, sorry.
Welcome to the Types 1 session. So for the first talk, Matthew will tell us about extensible data types with ad hoc polymorphism. So please go ahead.
All right, thank you very much. So this is work by myself, Yanning, Ara, and Ningning. All right, so extensible data types and type classes are two features of type systems for describing modular code. And these two features have both been studied in a lot of detail in isolation. And the types of modularity that they let us describe are different. So our motivation for this project was a lot of the types of boilerplate code that you often have to write require some powerful modularity, and we are hoping that by combining these two features, we could describe these types of boilerplate code in nice and generic ways. So in this presentation, I'm going to describe the language that we came up with and describe how we fix some of the problems with the simple approach to combining them, which runs into some issues. Okay, so first I'm going to start off with some background on what extensible data types are, since they're less common than type classes. So say, for example, we have this really simple record type here, which I'm using slightly different syntax for, and we'll see why I'm using that in just a minute. And it has two fields, a min field of type string and an age field of type int. All right, and here's an example of a term of this data type. This is a picture of Yanning's cat here. And let's say, for example, that we want to write a really simple function that operates on this data type. So here, this function takes a pet as input, and it projects out the name field using the / projection operator, and then converts it to uppercase and returns it. So this function works perfectly fine for the purpose that we wrote it for. If we apply it to Amber, then we'll get the result we'd expect. But you'll notice if you look at the body of this function here, that the only thing that it actually requires about the input is that the input needs to have a name field, and that field needs to have type string. And so the annotation of pet here is actually much more restrictive than it needs to be, because it specifies the full set of fields that's present. And if, for example, in our code we had a use case where we wanted to extend pet with some extra fields, or maybe we instead have like an owner class, or sorry, an owner record type that also has a name that we might want to apply this to, well, this function wouldn't work because the annotation is too restrictive. And so we'd have to duplicate the function and give a different annotation. But we could solve this if we could adjust our type to be less restrictive. So essentially what we want to say here is that the input should be any record as long as that record has a name field of type string. And so using extensible data types, we can do this. So this is the first way that we have to adjust our type syntax here. So instead of requiring this pi record syntax to be given all as one thing with a concrete list of fields, we're going to split this up into one piece of syntax that describes some record with fields given by tau here, and this piece of type syntax is going to have kind star. And then we'll have a separate piece of syntax for giving a list of entries, and we'll refer to this as a row, and it has its own specific kind. So by combining these two pieces of syntax together, we can give the definition of pet that we already had before, but the more interesting thing that we can do is we can introduce type variables and use them with the first piece of syntax. And so this lets us state the first part of the type that we wanted for this function, which is that we should have any record as the input. And so here we're being abstract about the fields that our input will have. But this type signature is still incomplete because now it's too general, because we actually need to be able to perform the projection of name in the body. And so to fix this and to restrict our type signature here in the way that we need to, we're going to introduce this extra piece of type syntax. So this less than squiggly is a constraint which says that tau0 and tau1 should both be rows, and the set of entries in tau0 should be a subset of the entries in tau1. And then by using this piece of syntax, as we have on the screen here, we can ensure that this projection of name will be justified, because however A is instantiated, the fact that this constraint is present will ensure that the name field is there and has the right type. Okay, so that's the first example. Now I want to give a second example so we can see the other type of row constraint that often comes up. So here we have a function that's similar to the previous one, except for instead of just returning the uppercase name, we're going to replace the name that was present in the original input and then return a new pet with that uppercase name. And you'll note here that in the body, instead of just mentioning name, we actually do have to mention the age field here because we're copying it into the output. But this explicit mentioning of that here is really not something that's morally necessary, right? Because really the only thing we're doing is changing the name field. So it would be nice if we could express this in a more modular way also. And so this is the constraint that we need to introduce into our type system in order to do this. So this constraint here means that all three of the taus should be rows again, and the entries in tau0 when concatenated with the entries in tau1 should produce the entries in tau3. And then by using this constraint, we can rewrite the function as follows. So you'll notice here we're quantifying over two different row variables. A here represents all of the entries that are present in our input and output, and B is all of them except for the name field. So now, because this constraint holds, on the term level, we can use this plus plus concatenation operator to combine the record with just the name field here together with P after it's been annotated with the type that just has the fields from B. And this annotation of P here in the body is also justified by the fact that this constraint holds, because if name and B concatenate to A, then we can just discard the name field to convert P to a record of B. Okay, so that's extensible data types in isolation. So now I want to give a really simple example that combines these two features together so we can see the different sorts of modularity that they enable. So here's another really simple function again that's written for pets, and we can make this more modular. First, by doing the thing that we did in the first example, where we get rid of the explicit mention of the pet type, and we replace that with a type variable and add a containment constraint to ensure that the projection of age that we're doing here is justified. And you'll notice that there's a second thing here that we can do to make this more general. So the operator that we're using in the body here on the age fields, the greater than operator, doesn't specifically require that the input should be integers. It allows any type as long as that type has an instance of the ORD type class. And so we can further make this type more modular by replacing this explicit mention of int with a type variable b here, and just requiring that that type variable must implement the ORD type class. And one thing that you'll note here is that the constraint for the containment, as well as the constraint for the type class, appear in the same position syntactically. And this is because in our system, these two constraints are the same sort of thing. They're all just constraints. Okay. So I hope this example shows how the two different sorts of modularity that these features give us are different. Here, row polymorphism is letting us describe a type that's generic over the fields of a record. And we can also use this feature for talking about generic cases of variance, though I won't talk about that too much in this talk. And then type classes here are letting us describe a type that's generic over some group of types that support common operations. In this case, the greater than operator. Okay, so that's one simple example. Now I want to go on to a more complicated example, which is also much more powerful and interesting, I think. So here we have this sort of boilerplate that you might commonly write when dealing with records. So this is an instance of the ORD type class for the pet data type. And what we're doing here is we're going through the fields and comparing each of the corresponding fields in the input. So first the name, and then the age. And then at the end here, we look at the result of the first comparison. And if that was EQ, then we're going to fall back to the result of the second comparison for age, but otherwise we'll prefer the first result. And so this sort of approach to defining ORD is, very straightforward, and it's basically always the same for any instance of ORD that you want to give for a record. And so it would be nice if we could do something to avoid requiring the user to write this manually. And there are features in existing languages that do this. So for example, deriving would automatically generate an instance that would look basically exactly like this. And that works for the ORD type class, but it requires some special work inside the compiler to support this. And so it's not the easiest for users to support deriving for new type classes they might define. So here in this example, we're going to see how we can define a very generic instance of ORD using the combination of these two features in order to make it easier for users to define these sorts of generic things. Okay, so just to summarize, in these sorts of instances, the approach that we're going to take is we're going to iterate through the corresponding fields of the inputs, and then we're going to aggregate the results in some way. All right, so here's the outline of the instance that we want to define. So you'll see here that I've left the implementation on the term level blank, and then also there's a blank here for the prerequisite of the instance. So like I said, the thing that we're going to want to do is go through the fields of these inputs and compare them all. And so in order for that to be possible, we need to actually have the required type classes, in this case ORD, to make that possible. Now, if we were just implementing ORD for a list of A, for example, then writing the prerequisite would be straightforward, because A would just be a type variable for a normal type of kind star. And so the prerequisite would just be ORD A, and then you could compare all the elements in the list. But here, A isn't just a normal type variable, it's a row, because we're using it with this pi syntax here. And what we actually need is for ORD to be satisfied for all of the fields inside that row. And so we're going to have to introduce a new constraint to be able to express the prerequisite that we need here. And that's the all constraint. So the meaning of this constraint is that tau0 should be a type level function that returns a constraint, and tau1 should be a row. And then this constraint will be satisfied when all the entries in tau1 satisfy tau0. So to give some examples here, if we have all ORD for the row that the pet data type is based on, this would be satisfied because we have instances of ORD for string and for int. But all ORD for this row here with the function type would not be satisfied because there's no instance of ORD for int to int. Okay, so if we take this new piece of syntax and we put it as our prerequisite, then this will give us the guarantee that we need in order to be able to compare all of the fields. So that's the type level stuff handled. But actually, there's a problem that I haven't mentioned so far, which we have to deal with now. So I've been previously talking about how we're going to want to go through the fields and compare them. And we'll start with our first field as having the highest priority, and then we'll fall back through the other fields in case earlier comparisons result in EQ, and so we don't have an exact decision yet. But in order to do that, we're going to want some consistent ordering of what that first field is, right? And we might assume that this is obviously going to be guaranteed, but there's an aspect of extensible data types that I haven't mentioned yet, and that's something called commutativity. So I have two comparisons on the screen here, and you might expect that the first one should result in the result true because A comes before B, but the second should be false because 3 is not less than 2. However, the part of row types that I haven't mentioned yet is that we often consider rows with the same set of entries to be equivalent, even if the entries aren't given in the same order. And the reason for this is that it's really convenient for users, right? If you're projecting things out and concatenating things together, it can be really tedious to ensure that the order always matches up everywhere. And so by having this equivalence, we make things much more convenient. But the issue with this in the context of type classes is that all of these 4 record terms that you see on the screen here can then be given a record type based on either of the 2 rows that are given here in this equivalence relation because of commutativity. And so the issue with this is that the behavior of the code that contains the type class, it depends on like how that type class instance gets resolved. But since these terms can be given 2 different types with different rows and different orderings of the entry, we can resolve that instance in 2 different ways, one for each of those types. And in those 2 different resolutions of the type class, different fields will be compared first. And so what this all means basically is that depending on which type we pick for resolution, we can get behavior for either of these 2 comparisons, which gives either result, depending on which field is first, which is obviously a really bad problem because, yeah, we have essentially non-determinism here, depending on which type we pick. Okay, so the easiest solution here would just be to say we're going to get rid of commutativity altogether. But that's really not ideal because one, for example, like I mentioned earlier, it's really convenient for users. And second, there's a lot of type classes where the order actually doesn't matter. And so we'd be imposing this restriction for no reason. So for example, the EQ type class, when we go through the fields, right, we'll compare them all for equality, and then we'll aggregate the results by just ANDing all those individual comparisons together. And so since that AND function is like mathematically commutative, it doesn't matter what order we do the aggregation in. And so in that case, we can allow for commutativity, and it doesn't matter which row type is picked for resolution because the behavior will be the same regardless. So the solution that we chose instead was to allow the user to control whether or not commutativity takes place for specific record types. So here we have this piece of view syntax that we introduced, and it can either be N for non-commutative or C for commutative. And then the Pi syntax here has a place that U can be given to specify which of the 2 cases we should work with for this record. There's one other aspect to this that I'm not going to go into too much detail here, but essentially we can have something called commutativity polymorphism also for functions where either option is allowable, but we want to preserve information about commutativity between input and output. But yeah, I'd recommend reading the paper about that because we don't have time to go into that here. Okay, so now we can finally go back to our instance that we're trying to define. And if we add the N indicator on our record here, then this will resolve our problem for this instance. Oh, okay. So now that we've resolved that problem, we can actually implement the term. And we can do this by introducing a new primitive on the term level. So this primitive int here is short for induction. Essentially in this context, you can think of it as a fold. There is a good reason why it's called induction, but that goes into some details of how the types work that I won't talk about in detail here. So basically, the first argument here is a type argument, which is the row that the fold is going to be performed over. So in this case, we're going through the fields in A, and so we provide that as the first argument. The last argument here is the initial value. So if we're comparing 2 rows that have no entries, right, the empty rows, then we want to start out with EQ as being our initial result, since those will be equal regardless of what instances of the term it is. And then finally, this second argument here is the most important. This is the folding function. So this will get invoked once for each entry in A. And at each point, the first argument will be the label for the current entry that we're operating on. And the second argument will be the accumulator that we've built up so far. And then in the body of this function here, we're going to call the other helper here that we have at the bottom of the screen, which essentially just looks at the first argument and checks if it's something other than EQ and prefers that if it is, but otherwise it falls back to the second argument. And here as the second argument to fallback, we're going to compare the current fields that we're looking at based on L in X and Y. And yeah, this is the whole instance. And this applies to any record where all of the fields implement the ORD type class. So there's two really important things that I want to point out here. So in the earlier examples that we saw with extensible data types, we always justified the operations that we were performing, such as projections, by the fact that certain constraints held. And so here in the folding function for end, it's going to make sure that there are constraints that are present in the type of that, which justify this projection here by giving a relationship between the row A and the entry with L and some other type corresponding to that name. And so this is what justifies the projections that we're performing out of X and Y here. And then second, so you'll notice we're also performing the comparison on those two results. And this is also justified by the fact that that relationship between A and L holds, as well as the fact that this all constraint holds. So by combining those two pieces of information together, we can infer the fact that the type corresponding to L in the row A implements the ORD type class. And so this justifies the fact that the comparison is allowed in the body here. Okay, so that's the general idea of our system. So to sum things up, basically the naive combination of row types and type classes results in the non-determinism that we saw. And we fix this by introducing different commutativities and a hierarchy within those so that the user can control for exactly the behavior that they want in the cases that they're dealing with. And second, by combining these two features together, we allow for some really powerful new constructs, such as all and end, which we saw in the previous example. And there's lots more in the paper, so I'd recommend reading it if you're interested. We deal with rows that are used to construct variant or sum types. We also have higher-kinded rows and two other constructs for working with rows, lift and split. The semantics of our language are defined by elaboration. So in the paper, we describe our target calculus, which has some interesting properties of its own. And we give the full description of the elaboration that converts from our source to that target. In our artifact, we have proofs in the Lean4 proof assistant that guarantee the properties we want from our elaboration rules and our target. And finally, in the paper, we evaluate our source language using the Brown benchmark for tabular types, which has a bunch of functions that are useful for working with tabular data. And our system is really useful for working with that sort of data. And so we show that we can implement almost all of those functions. Yeah, that's everything.
All right, thank you. So we have many questions.
Thank you. I have two questions, but should both be quick ones. So the first question is, you have this example where you use all fields so that you ensure that every field in this record is comparable. But what if I have a data type where some of the fields is only some of the fields is comparable, and I want to restrict my comparing operation to this subset of fields? Is that expressible by your, like, can you compose your constraint language to allow this kind of expressiveness? And the second question is, do you think if I want also parametric polymorphism, does your method scale, or what the possible difficulty you could anticipate? Yeah, thank you.
So maybe I'll start with the first one. So yeah, that's a very good question. You could think of maybe implementing this instance using a concatenation constraint and just requiring all for one part of that. But the issue with that is if you express it like that without any other details, a valid resolution of that is just to make the part of the concatenation that implements the all of ORD the empty row, and then everything else will just be considered part of the rest of the row. So what you could do instead, though, is you could implement a second function that has to be invoked explicitly, and then you can provide as input some sort of indicator, which specifies the sets of things that you expect to be comparable. And then, yeah, you could do what you're describing. And we do have an example in the paper where we do this with EQ. So yeah, I'd recommend reading that. And in terms of the polymorphism, parametric polymorphism, maybe we could talk about that afterwards. Hello.
Thanks for a nice talk. I guess I have two questions, very naughty of me, as well. But the first one is, this seems very closely related to the work of Garrett Morris and James McKenna.
Yes.
The ROSE system.
Yes.
Can you say something about that?
Yeah, so we're building on their work here. I meant to mention that earlier in the talk. But yeah, the presentation of extensible data types that we're using here is based on their 2019 paper.
Great. No, it's really nice to see something practical being built on top of that. The other one is, have you thought much about doing effect typing?
We haven't, no, sorry. Thanks.
Thank you for the interesting talk. I had a question relating to the constraint language and so if it's built up as you have parametric polymorphism and so on. Have you had experience with whether this produces sort of useful or nice type signatures from a user perspective, or whether they're easy to infer and so on?
Yeah, so in terms of the type signatures that this produces, one thing that we have as context for that is the implementations that we did for this Brown benchmark for table types. And yeah, I'd say that it depends on the function. There are definitely cases where, yeah, it's very straightforward, but there can be cases where it can be a little more convoluted to express exactly what you want there.
Yep, thanks. We have more questions, including online questions. So maybe I'll ask one of the online questions.
Oh, okay.
No, but please set up your computer, the next speaker, and I ask while he's setting up. So there was a question about whether commutativity makes sense for sums, and also about whether you really want to track commutativity or rather the order of traversals.
Sorry, can you repeat that second part?
So the question is, intuitively, instead of commutative or non-commutative products, I would like to think about ordered versus non-ordered traversals with the order given in the type.
Okay, so in terms of the first part, in terms of order for sums, yeah, so the context there is that while the order annotation is given on the product or sum type, this order annotation really controls how that row variable gets resolved. And so there's many cases, where you could have a function that takes a sum as input and returns a record as the result. And so, yeah, it's still useful to have ordering information with respect to sums there. In terms of the second part, I'm not quite sure if I follow the question, so maybe, yeah, you could follow up on that later.
Answer directly in the Discord channel.
Yeah.
Okay, thank you. Let's thank again the speaker. Right, so for the next talk, we'll see Let Generalization by Joseph. Please go ahead.
Research on Let generalization, polymorphic recursion, and variable minimization in Boolean-kinded type systems. So a Boolean kind is a Boolean algebra at the type level, and we extend Hindley-Milner with Boolean kinds to facilitate fine-grained type inference for a variety of properties and features. Our running example will be nullable reference types, and the problem that we're solving will make more sense once we see the example. So nref is a type constructor. Its kind is ml to bool to ml. ML is just the normal, regular HM kind. Bool is a new kind that we're adding, and its inhabitants are 0 and 1. Okay. If nref binds a 0, it means that that is the type of a nullable reference. If nref binds a 1, that is the type of a non-null reference. Okay, so we introduce some operators, make reference. Alphas are ML variables, omegas are Boolean-kinded variables. Okay, and we have omega b. We have omega b we have nref bind in omega instead of a 1 because we want to allow omega to instantiate to being a 0 or a 1 as needed, because we can always use a non-null reference as though it's nullable. Okay, so we have null reference, and we have operations for reading and writing references, right? We enforce that the reference being, that we're reading or that we're writing to is non-null. That makes it safe. All uses of the signature are safe. You can add an unsafe, operator if you want. And so far, everything is syntactic. So everything so far can actually be checked with like syntactic unification. Okay, so we make some space and we introduce some new operators. First one is no coalescing. Okay, R1 coalesce with R2. If R1 is null, we return the right reference. Okay, the result is non-null if either input reference is non-null, and we could express that relationship right in the type using the Boolean connective. Okay, we can introduce a bind operator that has the opposite relationship. Okay, so let's walk through an example. What is the type of wand? We are dereferencing R1 coalesced with R2. So if you think about this example, if the left reference is nullable, right reference better be non-null. If the right reference is nullable, left reference better be non-null to guarantee that we can always extract the contents. So we have this one stuck case, and we need a principal type that can somehow express the interdependence between the nullabilities of these two references. Okay, so let's walk through type inference. Okay, so in classic HM fashion, we have that the argument to the dereferencing operator is equal to, that type is equal to the type of the result of no coalescing. That creates a type equation. Okay, injectivity of syntax, we get two subproblems. Right, we use syntactic unification to solve the syntactic problem. We use Boolean unification to solve the Boolean problem. Okay, and we can get our principal type that expresses the relationship, right, between the nullabilities. Okay, so to reiterate, we can use Boolean kinds of track properties. We could have Robinson unification defer to an equational unification algorithm for type inference. Okay, SAT algebras are also Boolean algebras. So, for example, take this record system from Kennedy. We can use we model or we type records as sets, and so record concatenation sort of has this relationship with union at the type level. Okay, so property tracking corresponds to Boolean algebra over 2. Width typing corresponds to powers of 2, and there's real research being done recently by the FLIX, by FLIX researchers who use Boolean-kinded types in the design of the FLIX programming language, right? And particularly important is the recent work on qualified types, which sort of condenses a lot of previous work on type-level properties. It's pretty nifty. Okay, so past work has subsisted on Boolean unification to support basic type inference. Okay, but we might want to do more. For example, let generalization was open. So in this presentation, we'll develop methods for local let generalization, polymorphic recursion, and variable minimization. Okay, and this has some clear benefits: code reuse, expressivity, readability. Okay, so we use Boolean ring formalism. Okay, so plus is exclusive or symmetric difference. Multiplication is and or intersection. Okay, the Boolean kind forms a ring over the associated operators, the relevant operators. The important thing is just that anything plus itself is 0 because we're working mod 2 essentially. B denotes complete axiomatization of a Boolean ring. Okay, so polynomial form is a canonical form. What this means is that if two types, okay, row 1 and row 2, are equal up to axioms, we can normalize both of them to some row 1 tilde, row 2 tilde. And they'll be equal syntactically. If row 1 and row 2 are not equal up to axioms, they won't be equal syntactically, right, after we normalize them. Okay, polynomial form is more commonly called ANF. Okay, so it's rather clear that omega occurs syntactically in omega plus omega, but does omega occur up to axioms? Well, in order for it to occur up to axioms, it has to occur syntactically in all equal types. So in this case, omega plus omega reduces to 0. So we do not say that omega occurs in omega plus omega up to axioms. Okay. So in general, the variables which occur in polynomial form syntactically are exactly those which occur in the type, right? And there's a proof by contradiction. It just relies on this fact that normalization, that we have a normalization algorithm does not introduce new variables. Okay, so now does omega 2 Boolean occur in the type scheme for omega 1 plus omega 2? This is a more interesting question. We're getting closer to the research. Okay, so the answer is, Well, type schemes are equivalent if they're instances of each other, right? So if there's instantiations on the rank 1 variables that allow you to go back and forth. So we can say that, you know, the reference or the type scheme on the right is an instance of the type scheme on the left, and vice versa. Okay, so that we have that these type schemes are equivalent. They're instances of each other. And so we can say that omega 2 does not occur, right, in the original type scheme because it doesn't occur in the highlighted type scheme. Okay. And so, yeah, so omega 2 is not a free type variable, if it, you know, in the context of a type system. So we normalize type schemes such that all unquantified variables occur up to type scheme equivalence. So the idea here is that we're going to be computing eliminators, right, on quantified variables. We call those rank 1 variables. We're going to be computing eliminators on rank 1 variables that eliminate rank 0 variables. Okay. And we're going to work over collections of types, right? So in this example, we have 2 nrefs. Those each bind nullabilities. Those are shared. Those are under a single quantifier, right? That omega 1 is shared. So we have to operate over collections. Okay. So what is elimination? Well, an E-eliminator eliminates, right, the dependency of a particular variable from a collection of types, right? So in this case, you know, if you focus on the right, epsilon is eliminating the dependency on omega, but it cannot actually instantiate or replace omega directly. So you have to use, you know, nilpotence or item, you know, you have to use these different, you know, like annihilation, you know, to sort of be able to eliminate that dependency. Okay, and there's a reduction from Boolean elimination to unification from past work. Okay, and we care about this idea of preservation. So if we apply a substitution sigma or some instantiation, there's an instantiation on rank 1 variables back. So we say that it preserves the let generality. A substitution preserves the let generality if it doesn't actually change what the scheme is up to equivalence. Okay. So again, we are going to compute eliminators, right, on rank 1 variables of rank 0 variables, and we're only going to keep those that preserve equivalence. Okay, and so to normalize, we just repeat this process for all of the rank 0 variables until we're left with only the ones that are essential. Okay, order doesn't matter because everything is equal up to type scheme equivalence. So we can compute free type variables. We're halfway there for local let generalization. Okay, there's a second problem. See this context, we have omega 1 plus omega 2, right, as a nullability, and we have this typing. Okay, omega 1 and omega 2 both really occur in gamma. Okay, but we can apply this substitution. Okay, that substitution introduces this omega hat. The omega hats cancel in gamma, okay, but not in y. And so that's a new free type variable. Okay, we can form a type scheme around that. Okay, and that produces a more general type. Okay, so what do we have to do? We have to apply a substitution which reveals the polymorphism hidden in the context, right? And it turns out that there's always like a substitution which reveals the maximum amount of polymorphism, right? So we'll be able to have completeness. Okay, the problem is roughly that there are these extra derivations coming that are a consequence of the self matches on the context. Okay, and so we'll construct a substitution gamma which parameterizes these self matches on fresh type variables, right? And the new fresh type variables will form type schemes because they can't appear in the context because it's a self match. Okay, so basically what's going to happen is we're solving the self match context equation using something called Levenheim's method. Okay, so when the guard holds in this construction, gamma is going to be our B generalizer. Gamma is going to equal some renaming, some freshening operation when the guard holds. It's going to be identity when it doesn't hold, and that's able to parameterize a set of self-matches if you imagine new bar as like some arbitrary instance of some uninstantiated omega bar. Okay, so we show how to construct type inference with the required semantics in the paper. More details there. Okay, formally, a E-generalizer gamma obeys this criterion, which was specified by Kennedy in past work. If and only if two substitutions have the same effect on the context, there exists a way to extend sigma 2 into sigma 1, so to speak. There exists this extension eta, which makes it so that the entire right-hand side is sigma 1. And of course, if sigma 1 and sigma 2 do not have the same effect, then that extension cannot exist. So in our case, sigma 2 union epsilon will distribute sort of elegantly into our little gamma, okay? And to show that this works, we'll prove the forward direction and its inverse. Okay, if sigma 1 and sigma 2 have the same effect on the context, we can fix eta as shown.
then the guard always holds, and we'll have that the entire right-hand side reduces to sigma 1 because the if-then-else term will go to the true branch. Okay? If they have different effects on the context, okay, the if-then-else is going to be forced into the else part, okay? And since sigma 1 and sigma 2 have different effects on gamma, they must have different effects on the free type variables contained in gamma. Okay. So at this point, we can perform local let generalization, okay? You just do type scheme formation as normal after you apply gamma. And the next topic of interest is polymorphic recursion, right? Giving recursive calls access to their own type scheme. So we can define a list type as shown. Just the idea here is that if nlist binds E0, it means that all references are presumed nullable, but if it binds a 1, there must be a non-null reference somewhere in the list. Okay, the destructor must reflect, so there's sort of a gap between the constructor and the destructor. We can't presume to know whether or not it's the head or the tail that contains the non-null reference, so the destructor has this existential component to it. Find ref, we can define this iterated version of the no coalescing operator, and then we can just have this iterated version of the wand example that we started from. By the way, the wand, that name comes from the literature on record concatenation, and you could sort of adapt the problem there to nullable references. Okay, so we have this iterated version of the wand example, and we expect to be able to define these types, right? So if nlist binds a 1, there's a non-null reference somewhere in the list. So if we coalesce the whole list, right, we should be able to extract the contents. Okay, but it turns out that polymorphic recursion is necessary for the type of find ref and the type of deref list by consequence. So we annotate some types. In classic HM fashion, the type of the recursive call is equal to the type of the function body or the function definition. That creates this equation. This equation forces nlist to bind to 0, so we can't really presume anything. Okay, but it turns out that that is more, that's more special than we need. It just needs to be the case that the recursive call is more special than the type of the recursive definition, because we can always use a function in a more special way. Okay, that's the idea of let generalization. So in fact, we just need to apply a substitution such that the square subset equal, which says that the left is an instance of the right, such that that holds. Okay, and so it suffices to satisfy, right, this relation, as already stated. And in fact, there's a sense in which polymorphic recursion is actually a generalization of let generalization, right? If you have a sequence of like let expressions, right? Since polymorphic recursion is giving recursive calls access to their own type scheme, right? In a recursive block, each recursive call has access to all the type schemes in the sequence. Okay, so in general, polymorphic recursion, in general, polymorphically recursive type inference corresponds to solving semi-unification problems. Syntactic semi-unification is notoriously unsolvable. Boolean semi-unification is solvable, essentially for the same reason that SAT is. The satisfaction problem. Okay, so again, we have to solve over collections. And Boolean semi-unification is readily amenable to Baz's method, which is a semi-unification strategy with termination dependent on E. So justification is split into 3 parts. The first 2 points are sort of generic over E. The third is more specific. Okay, so we have Boolean semi-unification on the left. We have Baz's problem on the right. I guess the German is more like bots, but okay. If we look at this, we can very quickly see that that every solution to the semi-unification problem must be a solution to Baz's problem, because that sigma tilde on the right-hand side of the B semi-unification, that can just be a part of the residual substitution that's being hidden by that square subset equal operator on the right. Okay, so every semi-unifier is a solution to Baz's problem. That means that the most general solution to Baz's problem must encompass all of the semi-unification problems, right? And that means that we can always solve Baz's problem on a semi-unification system without losing any solutions, right? It's always going to be a superset of the solutions that we get out there. Okay, so now we have Baz's problem on the left. We have B unification on the right. We need a way to implement Baz's problem. How do we actually solve this problem? Well, if you look at it, we have, for Baz's problem, we have the sigma on the left-hand side. We have a residual substitution being hidden on the right-hand side. That looks a lot like unification. And in fact, if you just rename the omegas on the right-hand side to some new bar, it is unification. And you can prove it formally, but I think it's easy to see intuitively. The problems are equivalent, so we can use B unification, Boolean unification, as a way to solve Baz's problem. Okay, and an equation is solved, meaning that, right, so the semi-unifier is the identity function, so there just exists a match. an inequation is solved exactly when a most general solution to Baz's problem preserves the left-hand side of like the system. Okay, and so to see this, if the inequation is solved, we can just say that all solutions to the semi-unification problem are solution to Baz's problem, so we just say sigma equals identity, and therefore all most general solutions must be equivalent to an identity. Okay, if we go the other way, assume that the solution preserves the left-hand side, then we can see that the inequation must be solved, because if you just follow the arrows, it's mu sigma dagger. Okay, so there exists a match already. We invert both sides, and we can say that if we solve an unsolved equation, it must irreversibly narrow the left-hand side of, or you could just say that it must narrow the semi-unification system in some way. Okay, Boolean rings are finite. There's only a finite number of proper instances of any formula, so Baz's method must terminate. And this even works, this is even true for infinite Boolean rings due to their special structure. Okay, so we may now solve a system of inequations, and that means we can do polymorphically recursive type inference confined to the Boolean kinds. Okay, the last problem that we study is variable minimization. Okay, and so take this example. What is the inferred type? Well, it's this type following our methodology, but there's a better type. That's a better type since the references to 0 and 1 don't appear, we're not using them in any other way. They're confined by their scope to that expression. We don't need to separate omega 1s and omega 2s. We can just map them to some omega. Okay. Similarly, there are situations where, depending on what Boolean unification procedure you pick, you could get solutions of varying quality. Right? We might want to equalize, right, these different solutions. That's another application. So we'll solve the problem over collections, and then that can be extended to solutions over substitutions or contexts. That's all in the paper. Okay, so minimization basically amounts to trying to group like dependencies together behind some binary function phi. Okay, and once you've done that, it's very easy to compute the match from the left-hand side to the right-hand side due to the strict functional completeness of the Boolean algebra. That match must always exist. And that allows you to compute something that we'll call a one minimizer, which decreases the number of variables in the collection by 1. Okay? And so we can reduce the computation of one minimizers to Boolean unification. It's just like a bunch of math, okay? And so on the left-hand side, we have the original, we have our original collection. On the right-hand side, we have a new collection, and we have a phi binary function. Those are just like fully polymorphic, those are just encoded using unification variables. And so we just solve, and we ground the extra variables, okay? And the one minimizer is the solution to this matching problem. Okay, so we repeat this process for all variables, for all pairs of variables. And so if we have the B minimizer, like the full minimizer on the left, we can introduce this family of involutions, and we can degrade the B minimizer into a one minimizer by just making it worse and worse by having it introduce more and more variables. And so it's very easy to see that the B minimizer must be constructed out of one minimizers, and so there ends up being a way to inductively build it up. And so it suffices to just to compute it for all pairs, and you have to try all pairs. As it turns out, but fortunately the order is not important as everything is equal up to equivalence. Okay, so for implementation, we provide standalone implementations of all three procedures in OCaml. We also provide a reference implementation for an ML dialect which supports nullable reference types with local let generalization and polymorphically recursive type inference. Of course, the solutions of the paper generalizes to any Boolean kind of system. Additionally, we provide proof sketches for syntactic soundness as well as the correctness and completeness of type inference for nullable reference types in case there's any interest there. Okay, so in summary, we solve problems in type inference by procuring procedures for the corresponding problems in automated reasoning. Here's a table. There's this nice correspondence. And for future work, you can consider like more correspondences. You can consider other equational theories, right? Other algebras. You can consider new applications of Boolean-kinded types, so on and so forth. And that's my time.
Thank you. You have questions?
Thank you for the talk. I'm curious if have you considered sort of so you mentioned here the language features, sort of considering other algebras. I feel like Boolean algebra is a relatively rich structure. You have negations, for instance, and I wonder if you've considered what happens if you, for instance, only have a lattice? Do things get simpler, or maybe do they get harder?
They get way worse. So not every algebra has most general unifiers, right? We're sort of blessed with most general unifiers for syntactic unification, Boolean unification, abelian group unification, right? Some generalizations of Boolean group unification. Then there's some more obscure stuff like if you just have left or right-sided distributivity. But most theories do not have. Most theories just do not have most general unifiers, and so then there's a burden of type annotation, and of course complexity, it varies wildly as well, right?
Cool. I'll actually ask a similar question to the question I asked before as well. What did you think of the user signatures that you get in this sort of system? I don't know, you say you have an implementation, but I don't know if you looked at sort of some specific, if you tried to inferring types for specific programs, so you had some benchmark.
Yeah. So if you want, like the Flix programming language has like way more evolved, they implement, at least at some point, they implemented some version of their nullable references system. And so if you want to see like real world nullable or real world Boolean kind of types, you should see what they're doing over at Flix. It's really nifty. But yes, there is an implementation, and I think we must show some types in the paper to some extent. Like you saw the type of the wand example. It's at the very least there's an implementation, and you could definitely check that.
Thanks.
Okay. Next speaker, please set up your computer. And there's a last question, online question, which is: Are you planning to apply this work to Flix or some other experimental programming language?
So far there's not really any plans. The Flix people at the moment have a limited amount of time, and they're like ideologically opposed to let generalization. But who knows? It's So far no plans, but I might continue to develop my current implementation to something more evolved. Who knows?
Okay, great. Thanks. Let's.
Need help with the projector?
Yeah.
Here?
Yeah. Click here.
Not good.
Yeah.
Change.
Can you
it's already expanded.
It's already.
Entire screen. Yeah, good.
Okay.
Great.
Okay, so please go ahead.
Sure. Hey, everyone. Great to be here to share our research about type inference. My name is Xu, and it's a joint work with my great mates Chen and Shen. Shen is also present in the audiences, and our supervisor, Bruno Oliveira. We all come from University of Hong Kong. Let me begin with the first demystifying the title, since it's relatively short. Local contextual type inference, locally simple, because we are presenting a local algorithms. Contextual basically means, it's from my previous work called the contextual typing, which is a conceptual idea that generalizes over the bidirectional typing. And there's also a term hidden inside called the local type inference. And it implies two different angles to view our work. The first is this work is a direct extension of the contextual typing by applying its conceptual ideas to the polymorphic type systems. The second, this work can be viewed as a refinement of the local type inference by providing alternative but simpler specification and also removing some practical restrictions. I will cover two backgrounds first, and then we go to the main systems. Local type inference has been proposed by Pierce and Turner in about 2 decades ago. It's widely adopted by many practical languages, including the Java, Scala, C#, and TypeScript. It's considered as the partial type inference method, which means when program with a language that using local type inference, you are required to put a certain amount of type annotations to trigger or guide the type inference and type checking, which makes it scale to advanced features, including the implicit, imperative instantiation, and also the subtyping. Local type inference consists of two key ideas. The first is the bidirectional typing to allow the type information to be propagated from one node to its labeling node in the syntax tree. The second is, of course, the local synthesis of type arguments to allow you to write polymorphic function application without explicitly writing down a type argument. To my view, the local type inference is very successful, but there are still some places we can make even better. As you can see, below are the two function application rules for the local type inference. The first deals with function application with explicit type argument. The second deals with implicit polymorphism. As you can see, their functions are default uncurried and whose types are merged with polymorphic types, which make it farther away from the standard system like System F. And it has 4 application rules, whose instantiation logic is monomorphic, which makes the new researchers too hard to understand and extend. The third is their locality is limited to an argument of an uncurried application, makes it cannot propagate from the information from one argument list to another one. It's mainly due to, by the rule, it requires all the arguments in the list to be all inferable, which is very different from how practical languages behaves, because in practical languages like Java, it uses the instantiation information immediately in a left-to-right order, which means if you learn some type information from one argument, then you can use this type information to immediately to type check the next argument. Okay, great. Let's bring up to the second background. What's contextual typing? Let's think of a scenario. Suppose you are designing a bidirectional type system. For function application rules, you will face 2 choices. The first to inferring the type of function first, and check against the arguments, which gives the rule like this. And second option is the reverse. You first infer the type of argument, then you partial inferring the type of functions. What's the partial inferring? Because the E1, the function E1, only knows the partial information, which is type A here. And we have no good specification for this. The first direction is great. It's a default choice for many languages, and it's very useful for the higher order application. The second one is we have no suitable modes for the function, so I use a red question mark here, but it's still very useful for especially for the type inference with polymorphic function instantiation, where you wish to use the argument information to assist the inference of functions. And if you are even more ambitious, you want both in your system. You got the second trouble, which is backtracking, because 2 rules are just a syntax direct overlapped. Contextual typing is a work from 2 years ago that gives the solutions to 2 troubles. The first is how to find a way to specify the partial inference. It introduced so-called the contextual type assignment system, so-called the CTAS, that encourages do not use the modes, use the masks. What is masks really? In syntax, it's simple. It's just a sequence of 2 kinds of boxes. We have the transparent box and opaque box. Then you can decorate your typing judgment using the M here, which is a mask. The masks characterize what information we know from the context. Let's try some examples. If we have an opaque one, which means we see nothing in the context, and we use red color A here to indicate A is fully unknown. If the mask is a transparent one, we see everything in the context. We use blue color to indicate A is fully known. What if the mask is a sequence, then transparent, then opaque, which indicates the partial that input type A is known, but B is unknown? Then we can write the application rule in this way. You first analyze the argument and it type checks with a mask A, and we further propagate this information to the context mask of E1, the function part, by prepending this one to the M. then E1 is aware of more information. So the intuition is you can understand application rules works as the mask collectors. It collects more and more contextual information, and it can do more things. So the second trouble is backtracking. Our principle is in algorithm, do not decide the inference and checking of arguments in application. Decide it when it's consumed. I will not explain what's the notion of consume here. You can read the paper. But the key idea is that we introduce so-called the contexts, use sigma, and to store the deferred type checking tasks of the arguments. Here's the rule for the function application. You can see we have the context. We wish to infer a function application E1 applied to E2. We do nothing about the argument, but only prepend this argument to the syntax for the E1. So E1 is aware of more syntax, aware of more context, and they will analyze this information later. In the end, the two systems are proved to be equivalent. The specification using the masks, the algorithm using the contexts. And great, we are now equipped with enough knowledge to understand what's the local contextual type inference. It's a refinement of local type inference by using the contextual typing ideas. It gives rise to a modular design. If you compare this work and the previous work of contextual typing, you can see most of the typing rules are the same. Only the subtyping rules are modified to support polymorphic types. And just like local type inference, it advocates the so-called matching instead of the unification. We will get back to the matching later. It provides clear specification, making it closer to the canonical systems like System F or implicit System F. It removes the practical restrictions of local type inference and offers better locality. It's rigorously studied. Everything has been mechanized in the Agda and rock prover. To our knowledge, we are the first one to mechanize the local type inference algorithms in proof of systems. We hope it can stand as a principled and practical foundations for the inference algorithms and inference languages as a base model for the future researchers. Let's understand how our type inference works. Let's try to use a simple example, but with some hypothetical rules. We wish to apply the ID to the integer one. The ID is, of course, of the polymorphic type in the environment for alpha to alpha. And ideally, this function application has the type integer. So we apply the standard system application rule, which is here. We wish ID to have the type int, and argument have the type int. As you can see, ID has multiple types in the system. How to achieve this? How to achieve a term can have multiple types. Usually, we add a subsumption rule and a subtyping that states this polymorphic type is a subtype of this function type. This is sometimes also called the polymorphic subtyping, and this case is covered by one key rule called the four left rule in the literature that states that if you have a polymorphic type on the left, you can guess a type C and replace this polymorphic type with its substitution or instantiation in the subtyping derivation. This rule is great. It's very powerful, supports the implicit polymorphism, but unfortunately, the unrestricted four left rule is proved to be undecidable. So people often compromise to a decidable fragment. For example, the predictive type inference algorithms, they restrict the C to be monotypes only. So what's our version of restrictions? How do we achieve a decidable four left rule? Remember, since we are using the contextual typing ideas, this is only the hypothetical rules. Our typing derivation is just slightly different because we have the masks to decorate as the contextual information. We first start with the opaque one, since we know nothing, and then we analyze the argument. We opaque, but argument infers some information. This information will be propagated to the ID, and the function ID is aware of more contextual information, which is blue color int here. Then this information is further being passed to the subtyping and will be utilized by the four left rule. So here's our key insight. We can use the collected contextual information to ensure the guess can be safely met to achieve a decidable system. So here's the complete version of the 4 left rule in our system. You can spot 2 different differences between the classical ones. First is we decorated with a mask, which is a function mask, and the super type is a function type, which means in our system, the polymorphic types can only be instantiated to the function types, which exactly matches the key characteristic of local type inference that implicit polymorphism is application triggered only. And the second difference is we have an auxiliary judgment called the instantiability that guarantees us we are able to make the guess. What's the secret of this instantiability? I will illustrate with some slightly complicated example. We use the function f to apply it to 3 arguments, integer, lambda, and integer again. The f is of the following type in the environment, with 4 alpha, beta, alpha to alpha, beta, and beta as the output type. By using our application rules, because we want to collect more contextual information, we can collect the contextual information for the f, then f, we are able to make the guess for the solution of beta and alpha, and to make the following subtyping holds. So why we can do so? Why instantiability can guarantee we can save to make the guess? You can think of instantiability, it works as occurrence checking, but guided or constrained by the masks in a left-to-right order. The first is a transparent box, which means we know something in the context and we have alpha, so we can save to make the guess for the alpha. The second one is opaque. We see nothing in the context, but we learn this information already. For the previous argument, we are safe. Next, we repeat again. We have transparent one, we can safely guess the solution for the beta. We do not know information, but we learn this information already from the previous argument. We are safe, everything good. So essentially, instantiability does a left-to-right traversal of the masks and the types in a parallelized style. It is supposed to interleaved inference and checking of arguments because the first argument, whose type is inferred, and we check the second argument, third is inferred again. Great, so far we have a good specification. Let's move towards algorithm because we guess the type is not computed. We introduce a so-called the intermediate system called the matching subtyping that based on one key idea called the matching variables to track the solved instantiations. So we write our 4 left rule in this way instead of performing the substitution directly on the type A. We store it in the newly created environment delta. And the essence of matching variables is a solution cannot contain other matching variables, which is very different from unification because alpha equal to beta is strictly disallowed in matching. And we can have a very strong invariant, that is, matching variables can only appear on one side of subtyping. Not surprisingly, this is also implied by the original local type inference work. You can spot this premise. It gets a list of solutions, which is A over line, and it only performed substitution on one side is essentially the same with our invariant. Great. The second step to move towards the algorithm is we incorporate so-called the input and output environment because we still do not describe the computation process, how the solution is computed. We introduce the unsolved matching variable alpha. So when we have the for all left rule, then we just put the unsolved one in the alpha. Then we learn later, and we got some solutions in the output environment. You can see the sigma here, which is a little bit scary, but it comes from the idea of the contextual typing that sigma, remember, sigma stores the arguments, and we deal with it later. Essentially, how do we deal with the arguments? We can have two situations. If the information is not enough, we then try to infer. We use open to say this is not enough. We infer the argument, and we learn more information, and we use this information to further refine everything in the environment. Once the information is enough, we then try to check the arguments. As you can see, this process is essentially the same to the instantiability I illustrated in the before, because they all follow the left to right order, but instantiability explores the masks. Here, we explore the context. Let's try to run a simple derivation tree to get a big picture how the information flows in the algorithm. Here we use the opaque one to mean the empty environment, empty context, and we wish to infer the ID applied to the one. We do nothing but only prepend this argument to the context of the ID. The ID is of the following polymorphic type. We then try to compare this type with the context. It matches the shape of the four left rule. Then we create alpha, which is unsolved one, and we further analyze everything in the context to learn alpha is bound to the integer, and we also have the refinement of the types, which is further being propagated back at the instantiated type of this polymorphic type. This type is also the type of the ID under such context, and we use the output type, which is the inference result of this function application. Let's recap. I presented three systems. One's the specification on the right corner, and which just use a very simple rule utilizing a properly restricted for left rule. Then we introduced the matching variables to store it in the delta. And then we use the idea from contextual typing, and we designed the algorithm. Also, we incorporate the idea of the input and the output environment. In the end, the three systems are proved to be equivalent. And thanks to our very simple specification, we can be very easy to build a relationship to the implicit system F in the literature by proving the soundness and completeness. So let's conclude. We propose the LCTI offering a simple and modular specification of the local type inference. And we introduce matching subtyping that specify the use of matching in constraint solving. And we have concrete systems. We prove the soundness and completeness across three systems. Everything is at this GitHub link, including the mechanized proofs, Haskell prototype, and extended paper. That's all. Thank you. I'm happy to take questions.
Nice work. Does it extend to F sub, so where you actually have subtyping in the user?
Yeah, exactly. That's our next step. Yeah, so far we are working on system F, which is kind of the core system that can be extended to different directions. But F sub is definitely the next milestone of the work. Thank you.
Hi, thanks for the talk. The modes you have, they kind of look like moded logic programming, where you can kind of have things that have different direction, like information direction. Do you have any idea if there's a formal connection, or have you tried thinking about it this way?
Yes, we have the masks, right? And the modes is strongly the modes in bidirectional typing is strongly connected to the modes in the logical programming. And since our masks are generalized over the bidirectional typing, so it's basically if in some advanced logical programming, they have the advanced modes, I think they are just strongly connected.
Thank you.
Thank you.
Okay, we also have some online questions. So the question is, why is instantiability left to right? Intuitively, it looks like you could infer information from all transparent positions in parallel and then check the opaque positions.
It's mainly due to the first one is is efficiency. We just want to do one pass, and we do have some work that works on the got the information at once and then try to deal with it later. But maybe at some we do not sacrifice the efficiency. So that would be a open research questions. So yes, if we like refer to the backtracking, we can do so.
I don't think they implied to use backtracking, just to
one pass or two pass, like.
Maybe just one pass and some constraint solving. So that's also connected to something I wanted to ask, like how do you relate this system in terms of expressiveness with things like Haskell, which also do bidirectional typing?
Haskell is bidirectional typing. First, I'm not very familiar with how the bidirectional typing works in Haskell, but since we are just belong to the local type inference, and we do require some annotations, which makes the algorithm like very straightforward, just in this way. But I cannot give a very clear answers now.
Right. So the main advantage is that the declarative specification is very simple, right?
Yes. Yes. True.
Thanks.
Thank you.
Other questions? So there's a second comment on Discord, but I think it's more of a remark than a question. It says, isn't completeness sort of immediate? If you can add extra annotations to check everything, how would it fail?
Which completeness?
Yes, completeness. If you add extra annotations to check everything, I'm not sure what.
There is it offline. Yeah.
Yes, you can.
Sorry.
Offline. It's fine. Okay.
Thank you.
Thank you again. All right, so for the next talk, Daniel will tell us about typing strictness.
Thank you, and thank you everyone for coming. Today I'm going to be talking about my work with my collaborators at Penn on using type systems to model strictness. So in this talk, I want to try to answer three main questions. First, what are strictness and laziness? Second, why would we model them with a type system, and how would we go about doing so? And third, what properties would such a system guarantee? What benefit would we get from this approach? To begin answering the first question, I want to start by fixing some terminology. The words strict and lazy are used in rather overloaded ways throughout the literature, and I want to make sure that we're all on precisely the same page about what I mean when I use them in this talk. I'm going to use these terms in a couple of different but related ways, the first of which is as a characterization of evaluation strategies, not as descriptions of programming languages. A strict evaluation strategy is one that evaluates all expressions immediately as soon as they are encountered during execution. So for example, when we assign an expression into a variable, we evaluate that expression all the way down to a result before we do the assignment. Similarly, when we call a function, we evaluate the arguments before we perform the function call. The simple theoretical model for this is, of course, the call by value lambda calculus. Lazy strategies, on the other hand, operate differently. They only evaluate expressions when their results are actually used. So when we call a function, we don't evaluate the arguments until the arguments are actually used by the body of the function, if indeed they are. Similarly, when we assign an expression to a variable, we don't assign the result of that expression to the variable, rather we store a thunk, or a suspended computation, representing that expression. The simple theoretical models for this are the call by name and call by need lambda calculi. There are a variety of reasons why you might wish to use either of these strategies when implementing your programming language. Strict strategies tend to be more performant and more predictable, while lazy strategies are frequently more expressive, particularly when you're working with infinite-sized data, and can be faster in cases when you have lots of expressions whose results are only used on certain branches of execution. However, naively implemented, lazy evaluation suffers from a particular flaw. It uses a lot of memory holding onto the references to the various variables in use by the thunks in your program. So in practice, programming languages that want to implement lazy strategies will actually opt for a third approach, which is non-strict evaluation. This strategy straddles the boundary between strict and lazy by allowing expressions to be evaluated at any point between when they first appear and when they're used. In theory, this will give you both the expressivity benefits of laziness and the performance benefits of strictness. This is famously the evaluation strategy used by Haskell, and more infamously the evaluation strategy used by R. Okay, I'm going to put a pin in that definition for a moment. We will come back to it in a couple slides, but I want to briefly change gears to talking about another definition of strictness, which is as a characterization of variable usage. We say that strict usage of a variable is the kind that scrutinizes that variable. What does it mean to scrutinize a variable? Well, we're working in a lazy or non-strict setting, so variables can contain potentially unevaluated thunks, but certain ways that we might use these variables will require these thunks to be evaluated down to their top-level constructor. Think like adding numbers together, or branching on a Boolean value, or casing on a sum type. All of these require us to evaluate the contents of a variable down to their top-level constructor in order for us to know how to proceed with evaluation, what branch to take, something like that. This is what we mean by scrutinizing a variable. This is what we mean by strict usage. Lazy usage does not do this. This is using a variable in such a way that we don't need to scrutinize it in order to proceed. Think like putting a variable into a constructor or passing an argument to a function. An analogy that I find helpful is to think about variables like boxes that can contain potentially unevaluated expressions. Strict usage is the kind that opens the box, inspects the contents, and thereby triggers evaluation of those contents. Lazy usage, on the other hand, simply picks up the box, moves it somewhere else, frequently into a different box, but importantly does not open the box. So given this intuition, we can take a look at some programs in a simple call-by-name programming language and ask how they use their arguments. In this first case, this function uses its argument x strictly. In order to proceed with evaluation of its body, we have to evaluate x and its contents down to either true or false. We can't know which branch to take otherwise. On the other hand, the second function uses its argument y lazily. The just constructor does not require us to evaluate the argument in order to accept that argument. We can simply take y and whatever suspended expression is inside of it, put it into the just constructor, and return from the function. Lastly, however, we have the identity function. And, well, the intuition that we have so far doesn't quite work here. It's going to be important for later that this is considered a strict usage of the variable z, but the idea that we have so far doesn't quite tell us why this should be so. And in order to understand this, we're going to need to take a step back and connect our usage-based definition of strictness with our evaluation-based one from earlier. As I said before, the semantics of non-strict evaluation only require that expressions be evaluated at some point between when they are defined and when they're used. In practice, though, if a programming language wants to actually implement non-strict evaluation, it needs to make a choice about where this evaluation is actually going to occur. And typically, languages will do this via strictness analysis. Strictness analysis posits a hypothetical laziest possible evaluation of any given program, and then asks which expressions in the program can I safely evaluate strictly or eagerly, where safely here means without changing the observable behavior of the program relative to this laziest possible evaluation. Different languages might mean slightly different things by observable behavior. Think like throwing an exception or not terminating. What's important is that we don't consider things like memory usage or performance to be observable. Strictness analysis is allowed to optimize programs. To make things a little more concrete, let's take a look at some examples. This program here assigns the abort expression, which will fail the moment we evaluate it, into the variable x, and then we add 3 to x. This program will evidently fail immediately if we evaluate strictly. We will trigger the abort and fail. However, the program will also fail if evaluated lazily, just later during the addition, because the addition uses x strictly. We will need to evaluate x's contents here, thereby also triggering the abort. This program, therefore, has the same behavior in both a strict and a lazy evaluation. This other program, however, will behave differently if evaluated lazily. It will succeed, producing the value just x, where x contains a thunked abort expression. This will not fail because just doesn't evaluate its argument. It uses that argument lazily. So, in general, the key insight of strictness analysis is that the definition of a strictly used variable can itself be evaluated strictly, while the definition of a lazily used variable must be evaluated lazily. The connection between these two ideas gives us a unified definition of strictness, which we evaluate or express in terms of functions. We say that a function f is strict if and only if f of bottom equals bottom. Bottom here represents an expression whose value we cannot compute, whether because it throws an exception at runtime or because it doesn't terminate. The point is that if we give f an argument that we cannot reduce to a value, then the entire function call to f will also not be reducible to a value. This is the definition of strictness that you will most commonly see in the literature. I'm going to refer to it as extensional strictness for the rest of this talk, for reasons that I think will become clear momentarily. So with this new definition in hand, let's go back to our examples from before and ask, are each of these functions extensionally strict? Well, the first function is, if we pass bottom in as an argument, substituting for x, then we will be unable to evaluate the body because we cannot evaluate bottom to either true or false. Evaluation of the if statement will fail, f of bottom equals bottom, f is strict. G, on the other hand, is lazy. If we substitute in bottom for y, we will get the result just y. This is a constructor containing an aborting expression or a failing expression, but it is not itself bottom. G of bottom is not bottom, and therefore G is lazy. Then lastly, we can now more easily see why the identity function is strict, because it just directly returns its argument. If we give it bottom, we'll get back bottom. H of bottom is bottom. H, therefore, is strict. And this definition works pretty well. Compilers like GHC, for example, are able to use it to implement strictness analysis and recover much of the performance of strictness without compromising on the expressivity of laziness. However, the examples that I've shown you so far are almost trivially simple. Let's see what happens when we start adding a little bit of additional complexity to the programs that we're reasoning about. Let's take this Haskell program, for example. We might wish to ask, is this function extensionally strict in its arguments, f, g, and a? Well, the first thing that you may notice is that this uses a library function in its definition, the bind operator for the maybe type. And in order to even begin thinking about the strictness of this function, we need to know the strictness of this bind operator. And the only place we're going to be able to find that out is in the documentation. There's nothing in the program that will tell us this. And so we need to look at the documentation and hope that it will tell us, because if it doesn't, well, we're simply out of luck. If it does, well, then we'll know that this function is strict in f, but whether or not it's strict in g and a actually depends on the strictness of f itself. If f is not strict in its argument, its first argument, then this function will not be strict in a, and if f returns the nothing constructor instead of a just constructor, then g will never be called, and this function will be lazy in g. So we're going to actually have to inspect each of the call sites of this function in order to know what argument it gets for f, and therefore then be able to figure out its strictness with respect to its other arguments. So this analysis becomes inherently interprocedural, and ultimately we are forced to run what amounts to a mental abstract interpreter in order to figure out the strictness of functions. We need to substitute in bottoms for all the variables in our program and see what happens. And this is complicated, and as our programs grow and grow in complexity, it gets more and more challenging. It's also a little weird in cases like this one. This function is extensionally strict. Why? Well, it always fails, so it always returns bottom, and if f of anything is bottom, well then clearly f of bottom is bottom. But despite being extensionally strict, this function doesn't use its argument strictly, or at all. What's going on here? I thought there was supposed to be a connection between these two ideas. Something's a little bit weird. So at this point, it's worth taking a step back and asking, can we do better? Can we come up with a definition of strictness that more accurately captures our intuitions about what should be going on? Ideally, this definition will tell us more directly how arguments to functions are used. It will not require us to evaluate programs in our heads, even abstractly, and ideally also give us some reasoning principles about lazy functions. Right now, the extensional definition only tells us what it means for a function to be strict. lazy functions are those that are not strict. We don't have any properties about them other than that they aren't strict. So we'd like a definition that gives us some meaning behind laziness. Well, the fact that I'm up here talking to you may suggest that yes, we can do better, and we do so via the definition of intentional strictness, which we name in opposition to the extensional definition because while that one is defined in terms of a function's inputs and outputs, this one is more about a function's definition and body. And this says that a function is intentionally strict if and only if it uses its argument strictly. This sounds a little bit tautological, so we can rephrase to say that a function is intentionally strict if and only if its argument appears in a strict position. And this language should clue you into the idea that this is a syntactic approach to thinking about strictness. In each case, we can inspect where a variable appears in the program, whether it's a strict or lazy position, to figure out how that variable is used. Here, y, for example, appears as the argument to a constructor. That's a lazy position. This function is lazy. Here, the return of a function is strict. This function is therefore strict. Here, the guard of an if statement is strict. Here, the argument to this function doesn't appear at all in the body. We characterize this function as intentionally lazy. This, of course, gets a little more complicated, as it often does when you start introducing higher order functions. We have this if statement here, where the guard, as before, is a strict position. But the thing that appears there is the call fx. So whether this function is strict in its argument x depends, again, on the strictness of f itself. But unlike before, where we had no information available to tell us this, here we're going to get this information from the type of f. We're going to generalize this syntactic approach into a type and effect system that assigns each expression both a type tau and an effect gamma that describes the way that each program uses its free variables. Let's take a look at some examples. If we have some variable z with type tau in our context, then a bare usage of z will, of course, also have type tau, but it will also have an effect z strict that tells us that a bare usage of z is a strict usage of z. So far, so good. In the second example, we have x of type Boolean, and we have this if expression with type int that again tells us that this uses x strictly, because x here appears as the guard of the if statement. Here, however, just y, when y has type tau, will have type maybe tau, but this expression will tell us that it uses y lazily. Y appears as the argument to a constructor. That's lazy. But the type of this expression will also tell us that if we unwrap this maybe type and inspect its contents, that will trigger a strict usage of y. In general, in the intentional framing, this type of an expression tells us how its free variables will be used as more and more of that type structure is scrutinized. If we close this expression via an abstraction, we can now see how the type, or the lazy annotation for y, moves off of the judgment onto the argument of the function, telling us that this function is lazy in its argument, but returns a value that will use that argument strictly if you unwrap it. A little bit of eta reduction, and we can see that this is the type of the just constructor, which, as I have said at many points now throughout this talk, is indeed lazy in its argument. And then last but not least, we have this function that discards its argument and fails, and we characterize this as intentionally lazy. Now this is, of course, different than what the extensional definition would tell us here, and so it's worth asking, given this difference, what properties are we actually capturing with this new definition? What does it guarantee about variable usage? There are two properties here that we are guaranteeing. First, that intentionally strict variables are always scrutinized during execution, and second, that intentionally lazy variables are never scrutinized during execution. There is a third intentional characterization of indeterminate for when we cannot statically know whether or not something will be used at runtime, but we are only going to guarantee properties about these first two. Stated a bit more formally, the first property is strict failure, which tells us that a well-typed program will always fail if one of its intentionally strict variables is missing. If we imagine that we can evaluate a program that's open with an environment that substitutes values in for free variables, if this environment is missing an entry for one of the strict variables, then evaluation of the whole term will necessarily fail. You can see the connection here with the original extensional definition because you can imagine closing this open term via abstraction and then think of the environment like arguments to this new function. If this environment is missing a value, that's like a bottom argument, and the failure of this term is like a bottom result. F of bottom will be bottom if this missing variable is strict. The other property that we get is lazy soundness, which tells us that a well-typed program will not fail because its intentionally lazy free variables are missing. And this gives us a new reasoning principle. It tells us that if an intentionally lazy function call does fail, it's necessarily not because of the argument. This is useful, say, to a hypothetical programmer debugging a failure in their intentionally lazy function, because they know that the source of that failure must be the body of the function. They don't need to go look at call sites, because the type system will tell them where the error must be coming from. And only intentional laziness is strong enough to guarantee this. Extensional laziness cannot, because this function here is extensionally lazy. This, depending on the value of its first argument b, will either return its second argument x or the number 2. So if we substitute in bottom for x here, we will either get back bottom or 2, depending on b. So given that f of bottom is not always bottom in this case, we must characterize this as extensionally lazy. In the intentional world, we prefer to think of this as intentionally indeterminate, better reflecting the fact that we don't actually know how x is going to be used at runtime. We also saw earlier that the intentional strict failure property sort of implies the original extensional definition, and this is reflected in the fact that all intentionally strict functions are also extensionally strict. And then, in the category of intentional laziness, we can see that there are elements that are in both the extensionally lazy and extensionally strict categories, reflecting the fact that these two definitions are fundamentally capturing different things. Intentional strictness and laziness are really about how functions use their arguments, while extensional strictness and laziness are about the values that they produce. So, what have we done here? What does all this buy us? Well, we have decoupled the definition of strictness from the observable behavior of programs. And this has a number of benefits. First, it's just easier to think about. Instead of having to reason about two related but distinct properties at the same time, we can now think about them individually. It gives us more powerful reasoning principles, as we just saw. It's more intuitive in cases like this one that fail, irregardless of their argument. And also, because it's a type system, we can more easily surface it to users. One could imagine a programming language based on this that reflects the strictness of its functions directly in their types. Users wishing to know whether a function is strict could simply look at its type and not need to go consult documentation, which is, of course, fallible. This is, unfortunately, all of my time, but there is plenty more detail in the paper if you're interested, including formal statements of all the properties that I just presented here, the logical relations we use to prove them. Experts in the audience may be interested to know that we did all these proofs via an embedding into call by push value, which significantly simplified a lot of the reasoning here. There's a lot of redundancy in the cases of all the places where evaluation can be suspended. Call by push value sort of solves this problem by isolating all that reasoning to just the thunk case. We also have extensions to our type system to track additional information, and we mechanized all of this in Rock. I am happy to chat in extensive detail about any of this afterward, or take any questions that you may have now. Thank you so much for listening.
Hello, thank you for the talk. I was wondering about, so you've defined the strictness as a property of the function, but then in your explanation you track it in the judgment and also sometimes in the constructor, or sorry, in the type of the constructor. So I was wondering why this doesn't show up as a property of a function, as in you can give a function type which receives, it's an annotation of the function itself. So here you have it in this one argument, but then in the other ones you define it as something which is a property of the whole expression.
Yeah, so the effect, the gamma is a, the usage of all of the free variables in the term So if there's no free variables, like in this fourth example, then there's no gamma. But when you close a term that has free variables via an abstraction, the gamma, like the effects that were previously associated with those free variables now move onto the argument of the function, because like on some sense the abstracted term and the one with the free variables are like related that way.
So what about the annotation in the maybe?
So that is describing the fact that the maybe, like this maybe type will cause further downstream usages of y if you inspect it, like if you open it and then use its contents. So here this function type is telling us that while we're lazy immediately when you call the function, if you then take the result of the function and then use that and inspect the return type of the function, that will cause downstream usages of the argument.
I was just thinking that in there, I would have expected this to be a property of the just constructor, where the just constructor is a function, and then when you match on the just constructor, you would unpack the information about the y. Oh, right, there you are. Very good.
Hi, thanks for the nice talk. I was wondering why you defined in the type system version of this the return position to still be a strict position. You motivated this initially with your semantic definition. You also showed why that definition is flawed, so this doesn't necessarily carry over to why in the type system you still treated that strictly.
Yeah, the return of a function sort of, if you want the semantic connection, in order to motivate any of this, you have to assume that you're actually going to use the result of your program when it finishes executing, right? If you don't ever use the result of your Haskell program, for example, nothing will ever run. So you have to assume that the program itself is inherently a strict, like the outer term of the whole program is a strict position, which means that a bare variable also necessarily becomes a strict position. And then when you, again, connect that to functions by abstraction, that means the return of the function is also a strict position.
Okay, thanks.
So if I understand it correctly, so you need to record every free variables in each type constructor. So does it cause efficiency issues? Because basically your types will grow as your program size grows, and you need to duplicate these free variables for every layer. So have you done some maybe empirical evaluations on whether it?
We have not implemented this. Yes, the short answer to your question is yes. There is a very large annotation burden in this system. As presented here, it's more of a reasoning tool for like a new definition of strictness as opposed to like a practical proposal for a way that you could implement this. There is promising work in related areas of like how to reduce the annotation burden when you're tracking free variables like this. We haven't implemented that, but I think that is an interesting direction for future work to try to actually make this practically implementable.
Just a quick follow-up question. So is that true that you really need to duplicate everything for each layer of the type constructor, or that it can be collapsed or something?
That's sort of the question, is like, is there any redundancy that we can eliminate to make this a simpler problem, basically?
Yeah, okay, thank you.
All right, maybe a last question quickly.
Yeah, you mentioned that program optimization is one of the main applications of strictness analysis. So just wondering, does your new definition of strictness allow for more opportunities for optimization?
No, probably not. I think I don't have like a formal, like we've proved that it doesn't, but my guess is no. The benefit, I think, is that if you are a programmer trying to figure out why your Haskell program, for example, is not optimizing the way that you want it to, the only way that you can do that right now is to like basically dump the output of GHC and inspect what the compiler is telling you, and that's not particularly pleasant. So the motivation for this is like to come up with a way of thinking about strictness that's easier for people as opposed to like enabling more compiler optimizations.
Makes sense. Thanks.
Okay, thanks again.
Okay. Okay. Okay.
Hello, I'm Yifan Zhang from Peking University. I'm presenting on behalf of Zhentao Ye, who is unable to attend POPL'26 in person due to visa issues. This talk covers the paper, Accelerating Syntax-Guided Program Synthesis by Optimizing Domain-Specific Languages, which is a joint work between Zhentao, Ruyi, Yingfei, and Xin, all from Peking University. Modern program synthesis, especially syntax-guided synthesis, rests on two pillars: semantic constraints, which specify what the program should do, for example, input-output examples or logic specifications, and syntactic constraints, which restrict how it may be written, typically encoded as a domain-specific language DSL. This work focused precisely on that syntactic constraint, the DSL. Studies have shown that the choice of DSLs may significantly affect the efficiency of synthesizers. It follows a Goldilocks principle. Too general, the search space explodes. Too constraints, the task becomes unrealizable. Finding the sweet spot typically requires manual tuning by experts. Our goal is to automate this process. This work studies how to ultimately refine a DSL to accelerate synthesis on a target domain. The framework starts from a representative task set and iteratively modifies the DSL to reduce average synthesis time. But evaluating each candidate DSL by running the full synthesizer across all tasks is prohibitively expensive. So the key challenge is efficient DSL quality estimation without invoking the synthesizer. The solution is to estimate synthesis time using the enumeration ranks of feature components. Program fragments in solution programs whose positions in the grammar directly govern search space structure and correlate strongly with actual solver performance. Let me illustrate the goal of this work with a concrete example. Consider a single string manipulation task from SciGasComp. Given an input string that may contain an ID and metadata separated by a pipe, extract the substring before the first pipe. For example, TL-18273982 pipe 10M should yield TL-18273982. If no pipe is present, return the input unchanged. Let's solve this task using EU solver, a widely used synthesizer. EU solver works by enumerating small program fragments and composing them via decision tree learning. We start with a standard manually designed DSL, call it L0. It includes some basic atomic operators, such as concat, substring, index of, and if then else. Under L0, EU solver finds the solution P1. ITE contains X pipe, substring X0, index of X, pipe 0X. Now imagine a refined DSL L1. In L1, we introduce two operators, F1 and F2, which are macros for substring and index of, respectively. The raw substring and the index of and some other operators are removed. The solution simplifies to ITE contains X pipe, F1 X, F2 X, and X. Switching from L0 to L1 yields a 6.11 times speed up on this task, demonstrating how target DSL refinement directly accelerates synthesis. So the goal is to automatically discover L1. A natural approach is a search loop. Generate a candidate DSL, run the synthesizer on the task site, and measure speed up. But invoking the synthesizer is prohibitively slow. For instance, evaluating thousands of DSLs in the bit vector domain would take years. Hence, the central question is, how can we estimate synthesis time for a given task without running the synthesizer at all? Our key insight comes from observing how a naive enumerative synthesizer behaves. First, consider how to estimate its synthesis time. Such a synthesizer enumerates programs in order of increasing AST size, that is, by the number of grammar nodes, and check each candidate against the semantic specification. For example, input-output examples, until it finds a correct solution. Since checking a candidate program is roughly constant time across candidates, the enumeration rank, the position of the solution in this ordered sequence, serves as a faithful proxy for synthesis time. This rank-based estimation is designed for naive enumerative synthesis. But how do we extend it to solvers like EU solver? The key insight is EU solver constructs solutions by composing program fragments, and those fragments are generated by a model similar to a naive enumerator. Crucially, EU solver can only assemble the final solution after all required fragments have been enumerated. So the total synthesis time is strongly correlated with the time needed to enumerate the largest fragment used in the solution. We call this fragment the feature component. In our example, the fragments EU solver needs are underlined, and the feature component is substring x0, index of x, pipe 0. Since EU solver enumerates fragments by increasing AST size, we define the feature component rank as its position in that enumeration sequence. Computing this, we find the synthesizer must enumerate 3,158 programs before generating this fragment. So its rank is 3,158. We discovered that the feature component rank acts as a key predictor of synthesis time cost. This allows us to quickly estimate the synthesis time, and thus the effectiveness of a candidate DSL without actually running the synthesizer. If we know the solution program, we can simply calculate the rank of its feature component under a new DSL. This calculation is nearly instantaneous. By estimating the performance of the new DSL on each synthesis task based on the feature component ranks, we avoid the huge overhead of directly calling the synthesizer, thus making the cost of the automated search process acceptable. Now, let's revisit EU solver's behavior under the optimized DSL L1 from the feature component rank perspective. As before, we underline all fragments generated by the enumerator and identify the feature component as F1x, F2x. Its rank is 58. So the enumerator now needs to generate only 58 programs, down from 3,158, yielding a 6.11 times speed up. The sublinear speed up, that is 3,158 divided by 58, is approximately 54.4, but observed speed up is only 6.11 arises because EU solver's enumerator employs optimizations, such as observation equivalence, beyond naive enumeration. Synthesis time overheads, for example, decision tree learning, also contribute. In short, the feature component rank is a key predictor of synthesis time, and optimizing it drives measurable acceleration. We have shown that feature component rank predict synthesis time for EU solver. Do other synthesizers admit a similar notion? We analyzed state-of-the-art tools across Sega's benchmark domains. Dredsin on bit vector domain, Dude on string domain, and Polygen on CLIA domain. Though their algorithms differ significantly, we find that every solution can be decomposed into enumeration-derived fragments, and the largest such fragment is consistently the feature component. This universality lets us generalize our method beyond EU solver. For example, the underlined parts in these solution programs, generated by each respective synthesizer, are precisely those enumeration-derived fragments. Based on the feature component's rank, we propose a maze, an automated DSL optimization framework with 3 phases. Preparation: run the synthesizer once on the training set using the initial DSL, and collected all solution programs. Mining: extract frequent syntactic patterns from those solutions to propose additions. For example, macros like F1 and F2. Search: use a genetic algorithm to explore the DSL space, guided by feature component rank estimation, not actual synthesis. The core technical challenge is how to compute feature component ranks efficiently. First, for a new DSL, how do we obtain a candidate solution program without invoking the synthesizer? Second, even if we had the solution, enumerating up to its rank is intractable, as program count grows exponentially with size. For the first problem, we use rewriting. Giving a solution under the original DSL, we rewrite it into the new DSL using macro definitions, for example, F1 and F2. Since modified DSLs are conservative extensions, this rewrite is always possible. For example, substring x0, index of x, pipe 0, becomes f1x, f2x. When the rewritten program remains structurally similar to the true solution, its feature component rank serves as a tight upper bound on the actual synthesis cost. We periodically update this solution set by running the synthesizer to collect new solutions, refining our approximation. For the second problem, we design a dynamic programming algorithm that computes the rank of any program in time polynomial in its AST size, supporting both AST-based and term graph-based enumeration orders. We implemented a maze and applied it to optimize DSLs for state-of-the-art synthesizers through cross-validation. Our evaluation uses benchmarks from Sega's Comp 2019. 750 bit vector synthesis problems from the BV track for evaluating Dredsin, 209 string synthesis problems from the SLIA track for evaluating Dude, 100 CLIA problems, 82 from the general track, plus 18 softball by Polygen for evaluating Polygen, and all 1,059 problems combined for evaluating the general purpose synthesizer EU solver. Our research questions are: can a maze accelerate state-of-the-art synthesizers across domains by optimizing DSLs? How does a maze compare to existing DSL modification methods, which optimize for expressiveness or conciseness, not synthesis speed? Application study: what is the individual contribution of each core technique in a maze using feature components, and using enumeration ranks to end-to-end acceleration, thus removing either degrade performance significantly. The results show that a maze consistently accelerates state-of-the-art synthesizers across domains. On Dredsin, we achieved a 1.09 times speed up. On Dude, we achieved a 3.62 times speed up. On Polygon, we achieved a 1.53 times speed up and solved 3 more tasks. On the general purpose solver EU solver, Amaze achieved a 4.35 times speed up on average and solved 129 more tasks. As a baseline, we implemented a modified version of Amaze that simulates Stitch, a library-based synthesis approach, by minimizing the overall program size across a given set of solutions. Under the same setup, it achieves modest speedups on some synthesizers, but causes severe slowdowns on others, demonstrating that size minimization alone is not broadly acceptable and can harm performance for certain solvers. Finally, we conducted an application study to isolate the impact of Amaze through 2 core techniques: estimating synthesis cost using feature components instead of full programs, and using enumeration ranks instead of program sets. The results shows that both contribute significantly. Using feature components alone yields moderate speedups, though worse than full Amaze. Using enumeration ranks alone, however, leads to slowdowns on average. To summarize, we present a framework that transforms DSL's design from a manual art into an automated science. By leveraging feature components and efficient enumeration rank estimation, it automatically tailors DSLs to specific domains, significantly accelerating modern synthesizers. And thank you for attention. Zheng Taoye is currently exploring opportunities in industry. Feel free to contact with him after the talk. If you have any question about the paper, please contact the authors directly. Thank you.
So again, as the speaker wasn't an author on the paper, he's not able to answer questions. So we'll just dive right into the next session, the next talk. Oh, actually, we have. All right, so our next speaker is going to be Diyun Lee from Seoul National University. He's going to be talking about how we can accelerate sketch style synthesis by figuring out how to fill in the holes more intelligently. With that, take it away, please.
Let me start. Hello, I'm Do-Yoon Lee from South Korea, and I'll introduce my work titled Inductive Program Synthesis by Meta-Analysis Guided Hole Filling, co-work with Professor Woo-Sung Lee and Professor Gwang-Geun Lee. So let me first introduce what is inductive program synthesis is. There is input-output pairs given and also grammar constraints given. So the goal is to find the program which satisfies all input-output pairs. In this case, we can find two solutions and whatever okay when it is fine. And the problem is the exponentially growing search space. So we use bidirectional program synthesis algorithm, filling bottom-up components into top-down templates to make big program sketches in early stages. So here comes the hole. The hole means currently not filled, but grow into any program. And now we can see example partial programs here. While doing bidirectional program synthesis, we pick components and put into holes. So there will be partial programs with holes. When we see this, 2 times 2 plus 4, we should satisfy those input-output pairs, but we can find out that output numbers are odd. So is it feasible? Actually, no. We can analyze this by abstract interpretation, especially forward and backward interpretation both. The forward analysis will give whole as a top and whole times 2 as even. And backward analysis will give, we know output 3 is odd number and plus 4 will be minus 4, so there's whole times 2 as odd. So we have two constraints with whole times 2, forward, even, backward, odd. By meeting two constraints, it will result in both. So we can result whole times 2 plus 4 is infeasible for IO pair. Now here comes our observation. Hole filling order matters. In existing synthesizers, they doesn't consider real about hole filling matter just using left to right filling. But let's see this example. When we use left to right filling, 11 candidates explode. And when we use the right to left filling, we explode only 9 candidates. Because in real case, there will be more components and deep sketches. This difference will be exploded in exponential way. So we found it out that we can find preferred order in dynamic way for each situation. Let me take my idea by some analogy. Think about your racer. Before, we equipped straightaway booster, but still picking arbitrary routes, which means hole filling order. And now, we can choose routes to get more benefit from the booster. So we can ask a question, which route has the most straightaways? So we asked to the guide, and he said, I'm sending calls to count the exact number of straightaways. That takes forever, so we already asked, so can't you just use a telescope and give me a quick estimate? The guy said, I can't count the exact number, but I can identify routes that definitely have no straightaways. That will work, so at least we excluded hopeless routes, so the racer hope the time decrease. And that's our implementation. HOPE, an abbreviation of whole filling order prediction for efficient synthesis. And matching with analogy, existing booster matches with feasibility analysis, and telescope matches with feasibility scale analysis, which is meta-analysis, which with no straightways matches with whole filling order with no pruning benefit. And we can also figure out when the case all routes have no straightways, we can skip whole feasibility analysis. And let me explain more details. We implemented the algorithm using feasibility scale analysis and whole filling order recommendation, and also implemented new forward-backward abstract operators for the string domain. We support two domain, which is bit vector already as 2003, and new one for string, which is prefix and suffix domain with length. We also implemented some optimizations like multi-hole simultaneous filling or incremental analysis. Now you must be curious about performance. Yeah, we take the difference with other state-of-the-art synthesizers. Our implementation, HOPE, which is red, gets the best performance. This Sinfonia G is also Sinfonia, which is grammar-adjusted version for fair comparison. This graph is for cumulative time, so the lower line, which is ours, is the best. And for presenting our benchmark as a more general framework, we also tested in other domain, which is big vector domain. Also, in this domain, our implementation, HOPE, took the best performance. And there was a key result. HOPE uniquely solved 76 problems. And now I'll tell you the main idea. I first observed what makes feasibility analysis useless. And then I defined feasibility square analysis that predicts the usefulness, which comes from the first item. And then we should recommend the whole filling order by the feasibility square analysis. How can we do that? Yeah, for each O, run feasibility scale analysis with that whole hypothetically filled. In this concat example, 3 candidates will be there. Yeah, we run for each, and their result in rank 1 to 3. So we see the ranks and recommend which hole to fill first based on results. Let me go into the detail. What does the observation from feasibility analysis? The key observation is, infeasibility is detected when forward and backward results crosses, like even and odd meets and makes a contradiction as both. And another key observation, but never arises from one directional analysis alone. Yeah, it's just a single straightaway program. So if either forward or backward analysis returns top, then analysis cannot lead to pruning. Yeah, let me explain with exact example. These are useless cases. 2 minus whole times holes or 3 minus whole times whole will always produce top, because times whole we can't make constraints as even, but when we pick last hole to fill first, there is the case feasibility analysis result even, So that is not top. So might help cause may not produce top. And let me use this dotted hole notation to denote a whole field with something unknown but concrete. And now we want an analysis of the analysis that marks these useless cases as must have and might help cases as may not help, which we are interested in. So, jumps to the feasibility square analysis. It is the meta-analysis approach that analyzes the analyzer. Yeah, it's also an abstract interpretation. It predicts how the underlying analyzer will behave when each hole is hypothetically filled. It uses very simple domain, only may not have, must have, and but. A may not have means the underlying analyzer may return a non-top value, and must have means the underlying analyzer always returns top. By using this simple domain, we mimic the forward-backward integration of feasibility analysis. Yeah, forward feasibility square analysis mimics forward feasibility analysis. Hypothetical hole means something filled, so it will be constant, so we result in may not have. And regular hole means nothing filled yet, so feasibility analysis will analyze this as top. So feasibility square analysis will analyze this as must top. In backward feasibility square analysis, whole program will be analyzed by may non-top because it is output, and output is a constant. And other subprogram positions will initially must have and computed by the execution. Yeah, we compute forward-backward pairs to predict pruning potential. And recall, pruning happens when forward and backward meted and result in bot. And then, to recommend whole fielding order by this meta-analysis, we do the hypothetical whole filling. Yeah, for example, this concat example has 3 holes. So we just generate candidates with each hole hypothetically filled. First one, middle one, and last one. We perform feasibility square analysis on each candidate. And then we rank holes. Rank 1 holes is some position has may not have and may not have pair. This pair is forward result and backward result. This rank 1 evidence means we may prune the entire candidate. Rank 2s are especially whole positions which has must top and may not top. We can't prune the entire candidate, but we may infer preconditions for components to be filled at that hole. So this might help too. And rank 3 are other ones, no evidence, no pruning benefit. And there will be the admissibility guarantee. We prove this guarantee. If all holes are rank 3, we can skip underlying analysis. With example, yeah, when we use suffix domain inside, yeah, we use suffix domain and filling from right will work. Yeah, and in our algorithm, we make each candidate and do the feasibility square analysis. And the first one has no rank 1 or rank 2 evidence, so it will result in rank 3. And middle one has rank 2 evidence. Oh, it's a whole position. So we result this one as rank 2. And last one, which is filling from the right, is rank 1 because it has the rank 1 evidence. the root position in suffix domain, feasibility analysis will may analyze this as non-top, both directions. So it's the rank 1 evidence. So it has a rank 1 evidence, so entire candidate will be result in rank 1. By seeing this result, we'll pick the left hole to fill first. Let me discuss why this works. It's a very simple domain, just main non-type and must-type. Is such a lightweight feasibility square analysis effective? The answer is yes. We balance the analysis cost and guidance quality. Feasibility analysis itself is an already lightweight abstract interpretation, and feasibility square analysis is a further abstraction of the abstract interpretation. And also, it is precise enough to recommend effective hole filling order. And we proved formal guarantees. And see papers for details, but the key point is soundness and admissibility. Soundness means our feasibility square analysis correctly predicts the underlying analysis behavior. Yeah, we recall, we mimic the forward-backward iteration. And another key point is admissibility. If our strategy predicts no pruning, no other hole filling order can do better. This theoretical provenance is a strong aspect of our paper. With this provenance, and our strategy is also going to existing strategy in synthesizing. You just can adapt this framework to your ones. We did a lot of ablation studies, and let me tell one. This is a time breakdown of our implementation, HOPE. We know that when we get a good result by feasibility square analysis, that will make feasibility analysis more lightweight, but we can see overall result. Just seeing overall result, feasibility square analysis overhead is bearably small in both string domain and big factor domain. So let me conclude it. Battery issue. It's just a conclusion.
Well done. Let's thank the speaker. So we do have time for questions. If people are online, they can submit via Discord. Otherwise, just raise your hand.
Thank you for the great talk. Could you explain in the admissibility proof what you mean by one hole filling strategy being better than another strategy?
So our strategy is not an optimal strategy for hole filling order, but excluding hopeless orders. So admissibility guarantee proves this theorem. That's what was your ask?
I was asking what the definition of better means in the context of hole filling strategies, hole filling orders.
We define the predictable pruning power and define some hole filling orders for math symbols And we prove that our strategy finds the whole fielding order which has least pruning power. When our strategy finds some whole fielding order is hopeless, then any strategy should find out that whole fielding order hopeless. That is admissibility.
Okay, thank you very much.
I have one. Can you talk a little bit more about how you do this must not true, may true analysis? So your feasibility squared. Can you talk a little bit more about how you do that abstract interpretation? Does that work?
Can you speak more loud and slower?
Yeah. Can you talk a little bit more about how you do the feasibility, the feasibility squared abstract interpretation? How do you sort of determine, you know, if a term is a must true or a may not true, or vice versa?
Yeah, in feasibility analysis domain, there will be a top. And in our domain, we have may non-top and must top. So we analyze what will be the feasibility analysis result. So must top means the feasibility analysis must result in top. So this has a constraint, but may non-top, this is a top of our feasibility square analysis domain. This means no constraint.
And that has to be defined for every feasibility domain, is that right?
Yeah, when it is written in abstract interpretation style.
Are there any more questions from the audience? Let me check Discord real fast. There. Don't see anything. Well, if there aren't any more questions, let's thank the speaker again. Okay, so the last speaker of this session is going to be Jakob, and he's going to be telling us about how to improve bottom-up enumerative synthesis techniques. Take it away.
All right, so welcome to the presentation of our paper, Oriented Metrics for Bottom-up Enumerative Synthesis. And this is joint work with Roland Meyer, and I am Jakob Tepe. So the goal of today's talk is that we want to unify and generalize the existing approaches to bottom-up enumerative synthesis. So let's first talk about a problem that we can solve using bottom-up enumerative synthesis, which is syntax-guided synthesis, also called SYGUS. So in SYGUS, you're given a specification in the form of some examples, input and output examples. And these define the ground truth. And the ground truth transforms the inputs into their corresponding outputs. Then you're also given a grammar. And this grammar defines the search space of all the possible solutions. So the task now is to find a program inside that search space which implements the ground truth. Now let's look at a concrete problem instance. We have these input examples and these output examples. So we have to convert POPL''conf to POPL', RenCity to Ren, PLDI''conf to PLDI, and SoulCity to Soul. And we are also given a grammar. And this grammar allows us to return the input variable x, the empty string epsilon, conf or city. We can use the replace operator, which I will explain later, and we can use concatenation, which is just the usual string concatenation. And our task now is to find a program inside the grammar that converts each input into its corresponding output. The solution to this problem is the following program. I will explain this in more detail right now. So the R is an abbreviation for replace, and we can check that this is a solution by plugging in the first input example. So if we evaluate the inner replace operation on POPL''conf, conf, and epsilon, we replace the conf part inside POPL''conf by the empty string epsilon. This essentially deletes the conf part, and we're just left with POPL'. Then, in the outer replacement, we replace the city part inside POPL' by the empty string. But since there's no city inside POPL', we are just left with POPL'. Now we can plug in the second example, RenCity. We do the inner replacement first again. We replace conf inside RenCity by the empty string. Since conf is not inside RenCity, no replacement happens. We still have RenCity. Then we do the outer replacement. We replace city inside RenCity by the empty string epsilon, which just deletes the city part. So we're left with Ren. This works for the third and the fourth example in the same way, and so this is a solution to our problem. Now, how do programs come up with the solution automatically? And our first understanding is that existing approaches have a way to enumerate. So here we have our problem instance again, and bottom-up enumeration will start by enumerating the smallest programs which are inside the grammar. In our case, it's returning the input variable x, epsilon, conf, or city. So these are now the programs of size 1 in our current program pool. To generate new programs now, we use the operators which are allowed in the grammar to combine the programs we already have enumerated and get new programs from them. So if we apply this, we have no program of size 2, but at size 3 we can use the concatenation operator to get the programs x concatenated with x, x concatenated with epsilon, and so on. So every possible combination of the programs of size 1 using the concatenation operator. Now at size 4, we can use the replacement operator to generate new programs. At size 5, you have even more programs. Size 6, even more. And then at size 7, we eventually enumerate the solution that we've seen before. Now, as you can see, this has an exponential blow-up. Like, if we look at the sizes of the sets of programs, and if we don't use any smart method to shrink that size, then in the first program set of size 1, we have only 4 programs. At size 3, we have 16 programs. And at size 7, we already have more than 4,000 programs. And this is just for this simple grammar in this toy example here. Now, if we zoom a bit out and look at this more abstractly, we have our search space here and somewhere in there is the ground truth. And we just enumerated the programs along some enumeration order. And what we did is we enumerated the first ones of size 1, and then some bigger programs, so we enumerated them along their size. One trick you can do is use deduction, which was studied in various Cygers papers before. And what deduction does is the following. During the enumeration process, you've seen that we enumerated epsilon, city, then some more programs. At some point, we enumerated the program that replaces conference by the empty string. Then we enumerated some more. And at some point, we got to our solution. And now deduction realizes at this point, we have enumerated all the components of our solution. And it will just move up the solution in our enumeration order so that the solution is the successor of the last component needed to build the solution. So it's just a change in the enumeration order from this abstract point of view. Now the second thing that existing approaches do is they have a way to factorize the search space. Now, the first approach that was done towards this is the observational equivalence factorization, which was applied in 2013 to synthesis. And this states that two programs are observational equivalent if they behave the same on the given input examples. So program 1 and program 2 are equivalent if they have the same output on the given input examples. For example, the program X and the program X concatenated with epsilon will return the same output on the given inputs, and therefore they are equivalent. And this equivalence factorizes the search space. And we only need to keep one representative per equivalence class, and thus we can prune away many programs. For example, we have the program X and the program X concatenated with epsilon, and we only need to keep the program X. So X concatenated with epsilon can be thrown away. Now, if we apply this to the problem from before, then you can see that at size 7, instead of having more than 4,000 programs, we only have a bit more than 100 programs. So this has a significant impact on the search space. The next thing you can do is for factorization is abstraction. This was applied to synthesis in 2018, and the idea is to take the observational equivalence a step further. So instead of comparing the outputs, the concrete outputs of two programs, we first apply an abstraction function and compare the abstract output of these programs. So two programs are then equivalent if for each input their abstract output is the same. And this results in a coarser equivalence, and we still only need to keep one representative per class, and thus we have less programs to consider. Now, the second understanding is that existing approaches have a way to prune the search space. This was applied to synthesis in 2023, and the idea is to use a metric to define a ball around the ground truth. And then you only want to consider programs inside that ball. Now, this approach is deliberately incomplete. You might have pruned a program, so a subprogram of your solution is outside the ball, so you have pruned that, but you need this to build your solution. And if you've pruned the program, you can't build the solution anymore. But you can control this completeness or the speed up via the radius of the ball. So we can have this rather big radius, then we get more completeness, but less speed up. We can have this smaller radius, so we are more incomplete, but we have a bigger speed up because we consider less programs. Or we can find some middle ground. One downside here is that metrics require symmetry, but I'll get to that point later. Now, to sum up, the existing approaches have a way to enumerate, they have a way to factorize, and they have a way to prune the search space. Now, we can capture the enumeration by the enumeration order, which is a total order on the search space. The factorization can be captured by the equivalence, and the pruning can be captured by the metric we use. So these are the three parameters of bottom-up enumerative synthesizers. And our insight now is that the equivalence and the metric can really be captured inside one object, an oriented metric. So instead of three parameters, the enumeration order, equivalence, and metric, we only have two parameters, the enumeration order and the oriented metric. So now, what is an oriented metric? An oriented metric is a function that assigns a distance between two objects. And it has three properties. The first one is reflexivity. So from object A to object A, we should have the distance 0. The second one is that we are symmetric at 0. So if we have the distance from B to A of 0, then the distance of A to B should also be 0. The last thing we have is the triangle inequality. Now let's focus on this middle part here, the symmetry at 0. This allows us to be asymmetric. We only need to be symmetric at 0, but everywhere else we can allow for asymmetry. And we will see later that this results in better pruning. It also induces an equivalence. So with this we can express observational equivalence factorization and abstraction. So why do we want this asymmetry? The answer is that many Cygos operators, they exhibit asymmetric behavior. Let's look at a few examples. So we have the concatenation operator for strings, for example, and symmetry would require that the distance from the string POPL to the string PO is the same as the other way around, from PO to POPL. Now the concatenation operator, however, only works in one way, in one direction. It always produces superstrings of its inputs. Since POPL is a superstring of PO, we cannot produce PO using concat and POPL. But the other way around, since PO is a substring of POPL, it might help us produce POPL using the concatenation operator. So if we design a metric for the concatenation operator, we would like to have a big distance from POPL to PO, because concatenation doesn't help producing PO from POPL, but a rather small distance from PO to POPL, because with concatenation, we can go from PO to POPL. The next example is replacements with epsilon. So again, symmetry requires that from POPL to PO is the same way as the other way around. But the replace operator also only works in one way if the epsilon is the last parameter. So then we only get substrings of the first parameter. Now, since POPL is a superstring of PO, POPL might help us produce PO using the replace operator. But again, the other way around, PO is a substring of POPL. In this case, PO cannot produce POPL using the replacement with epsilon. Now, here we also want to have a small distance from POPL to PO, because we can go from POPL to PO using the replacement operator. But the other way around, we might want to have a big distance from PO to POPL. Now let's switch domains to the bit vector domain and look at the bitwise AND operation. So symmetry would require that the distance between the bit vector 110 to 100 is the same as the other way around, from 100 to 110. But the AND operation also only works in one direction. It always produces bit vectors which are bitwise less than its inputs. So since 110 is bitwise greater than 100, 110 might help us produce 100 using the AND operation. But the other way around, 100 is bitwise less than 110, and thus 100 cannot produce 110 using the AND operation. And again, we might want to have an asymmetric metric here. So we want to have a small distance from 110 to 100, but a big distance from 100 to 110. And that's why we want asymmetry. So the next point is the equivalence. Now, an ORI metric induces an equivalence at distance 0. So two objects, A and B, are equivalent if their distance is 0. We can quickly check that this indeed is an equivalence. So we get the reflexivity property from the reflexivity of the ORI metric. We get the symmetry property from the symmetry at 0. And transitivity follows from the triangle inequality. And with this, we can express the observational equivalence factorization and abstraction methods from before. So how can we design such an ORI metric? And the answer is that we first construct an ORI metric on the data domain, and then we can lift that one up to programs. So let's design an oriented metric for the replacement operator. The idea is that we want to reward superstrings of the outputs. So for two strings, I and O, we assign their distance from I to O as the difference in length if I is a superstring of O. But if I is not a superstring of O, we get a penalty of 100, and then we take the difference in length. Let's look at a few examples. So from PO to POPL, we now have a distance of 102. Since PO is not a superstring of POPL, we get the penalty of 100, and the difference in length is 2. The other way around, from POPL to PO, we have a distance of 2, because POPL is a superstring of PO, and the difference in length is just 2. So we have this asymmetry here, and also the intuition from before, as we discussed the replacement operator. Because we can go from POPL to PO using the replacement with epsilon, we have a rather small distance, but the other way around, we can't go, so we have a big distance. So now we want to lift this up for two programs, P and Q. And what we do is we evaluate the programs on the given input examples and then measure the distance there. So the distance from P to Q is P and Q evaluated on the input examples and the distance is summed up. Now let's apply this to the example from the beginning. We have the search space again, and we set the radius of our ball to 100. And now we might encounter a program like city concatenated with city. And we want to check, is it inside the ball? So we measure the distance to the ground truth. Now city.city always evaluates to city. The ground truth executed on the input examples will return the output examples, because this is the specification of the ground truth, right? So the ground truth will output POPL, REN, PLDI, and SOL. And since city is not a superstring of POPL, REN, PLDI, and SOL, the distance to the ground truth is greater than 100. And thus, we might prune this program. Now, if we apply this pruning and check the sizes of the program sets, then the last program set of size 7, instead of having 4,000 programs, we are only left with 900 programs. So we can prune quite a bit. Now, we can apply the factorization, and we factorize the search space by the induced equivalence of the ORI metric. And this is the same as the observational equivalence factorization. And now combining these two approaches, we're only left with 81 programs inside the last set. All right, now we've packed this whole thing into a framework, which is parametric in the two parameters from before, the enumeration order and the ORI metric. And as input, we have the grammar and the ground truth. And what we do is we first prune and then factorize the search space. Then we enumerate alongside our enumeration order. And then we might wind up with a program P, which is the correct solution. What I haven't shown you today is how to use abstraction with the ORI metrics. Then you might want to introduce refinement. And if you have a previous loop, a previous enumeration process, then you can learn from that previous enumeration process and get a different enumeration order. But for this, you have to read the paper. Now, in practice, we will instantiate this algorithm using concurrent instances employing different ORI metrics. So we might have ORI metrics tailored towards multiple operators. And we implemented this in a tool called Merlin and evaluated it on the Cygas benchmarks. So on the bit vector domain, we are 25 times faster than DrySynth, which is the next best tool on the bit vector domain. On the string benchmarks, we are competitive with the Synthonia string solver. Then we also compared against Blaze, which can also solve strings, and we are 75 times faster than Blaze. And against the baseline implementation, which does not use the pruning and does not use the learning, but you haven't seen that part, we are 42 times faster than the baseline. So to conclude, you have seen a framework for bottom-up enumerative synthesis, which is parametric in the enumeration order and the ORI metric. Then you've seen oriented metrics, which have the three properties: reflexivity, symmetry at zero, and the triangle inequality. And lastly, you have seen that implementing these has a substantial impact on performance. Thank you for your attention.
Raise your hand if you have a question.
Thank you for good speech. And my question is, what is exactly you learn? And like some constraints, like always be the superstring or substring, or the parameter like 100. What is the learning parameter?
Okay, the learning is, in practice, we say we have found a partial solution to the program in like the abstract space. And then with that solution, which works in the abstract, we will take the ORI metric and evaluate this solution for all the examples, so in the concrete space. So then you have this abstract solution, and we check if it's feasible or if it's a good solution in the concrete space. If so, we will enumerate it very early in the next iteration. So what we do is we change the enumeration order.
Could you say a bit more about how the interaction between two different or multiple ORI metrics works? So you presented them, depending on which operator you use, you prefer one metric or the other metric. So if I have a program that needs to use two operators with different, that have the flipped asymmetry, how would you do that?
Yeah, that's a good question. And currently, we are not very smart about it. So we just run different instances with different ORI metrics concurrently. And we don't care if we have, for example, the concatenation and the replacement operator inside the grammar. We just have one instance which runs with the ORI metric tailored towards concatenation, and one instance with the ORI metric tailored towards replacements. But this is future work.
Okay, thank you. Do you see a way to combine that, or having a more tailored ORI metric that switches depending on what the next operator is considered in the enumeration?
At the top of my head, I don't know how to change the ORI metric on the fly, but maybe that's a good angle to look at. Thanks.
Okay, thank you.
Hi, thanks for the talk. So you deliberately give up the search completeness, right? To my understanding,
yes.
You confine the search to a fixed radius. Is it fair to compare your tool against the other tools that guarantees the search completeness?
Well, we So in practice, our tool is also complete because we also run one metric, which is very trivial and which doesn't result in any pruning. So we have that as kind of a backup. But yeah, it's a fair point. Maybe it's not too fair to compare again complete tools. I don't know about that, but fair comment, Alex, I think.
All right. And you cannot apply oriented metrics for operators which are symmetry, right? Do I understand correctly? For example, addition is...
Addition would also,
addition operator, yeah.
If it's on the bit vectors, then you have a problem because you kind of can wrap around with the overflow, so you don't know where it come from.
Yeah.
If you would be on the integers, you would always know that you need less values. Like if I need to reach this integer, I can only get from lesser values. But with the overflow, it kind of corrupts that intuition, right? So we currently don't have an metric for the add operator.
Okay, yeah. And the last question is, can you find any insight that can be reused for defining oriented metrics for any new underlying operators in your paper?
Can you repeat the question?
Yeah, I mean, how much difficulty should we expect for defining oriented metrics for new underlying operators rather than Cygos operators?
Okay, so currently we only give an intuition in the paper, which is more than we gave in the talk. So having a streamlined way to do it is future work for us. The idea is to kind of try to measure the inverse semantics. So if you have a bit vector, which is very close to the solution and bitwise greater than the solution, then there are many other bit vectors with which you can use the AND operator to get the solution. But you might also have a bit vector which is, again, bitwise greater, but not so close to the solution, so more bits are different. Then there's only fewer other bit vectors which you can use the AND operator with to get the solution. So that's our intuition to kind of measure the inverse semantics. But we haven't done anything formal about this till now.
I see. Thank you.
And now I believe it's time for the poster session and the reception. So.